Ready to go? Okay. Okay, well, welcome everyone here. It's very nice to see all 10 of you here present physically. And I'm sure that there are plenty of people watching this virtually. My name is Chhabra. I'm from HPE. I cover the regional APAC region for HPC and AI. And this is one of the first ForCAST event in Singapore. We used to call this HPCAST, which stood for High Performance Consortium for Advanced Scientific and Technical Computing. And now we call it ForCAST, which is the For Community for Advanced Scientific Technologies, scientific and technical computing. So this is the first ForCAST event in here in Singapore and in APAC. And I welcome you all. Thank you for joining. And with that, I would like to sort of just let you know the agenda for today. The first speaker is from HPE. Can we flash the agenda, please? The first speaker today is from HPE. He's the Vice President and General Manager for High Performance Computing Business Unit, Mr. Bill Mannel. After that, we're going to have a few virtual sessions. Huang Pan and Jesse are going to talk about the GPU scaling, the AI development platform, and also about Slingshot. Moving on, we will have a very interesting session, which is one of the first in APAC for sure, and it could be in the world, where Hiew from NSCC is going to share his experience of using Red Hat on Cray systems together with HPCM. And that's pretty exciting as well in terms of his learnings and his know-how. We'll break for lunch. We all will go back to where in the main room where we are sitting, and that's where the lunch will be served. And right after that, NSCC sort of continues, where our favorite Paul Hiew will be presenting an update on the Aspire 2A. Following that, we're going to have a session from Steve Tolnai from Australia, where he's going to talk about the next generation of cooling systems, which is a very exciting topic because he's also going to share that how things are going in terms of the roadmaps a little bit with the CPUs and GPUs getting more and more power hungry, and what you need to do when it comes to cooling. And the last and not the least, there's going to be a panel discussion, which is probably the highlight of this event, where we're going to have panelists from HPE and NSCC, and also from Intel and Altair, talking about whether HPC is better, or the pros and cons of running it in public cloud versus on-prem. So that's the agenda, and we're going to have a closing remarks from Bill after that. But with that, let me invite Bill Mannel. Please come through. And just one liner before I invite him. In terms of, I know Bill for many years from SGI days. He used to be in SGI, and then he joined HPE. But he was instrumental having Cray joined into HPE as well. So I have known him for many years, and let me invite Bill Mannel. Thank you.
Well, thank you, everyone, both folks that are here. Nice to see faces for the first time in a couple years, as well as those that are joining us remotely. So as Raj was saying, I run the HPC business for Hewlett-Packard Enterprise Worldwide. And today I'm going to talk about our portfolio that's specifically built around HPC and AI. So first off, on the left-hand side of the slide, you see our are purpose-built supercomputing products. And so we'll talk about these in more detail. We've got the higher end, which is like the Cray EX line, and then some other specialty areas themselves that we'll go into, both for large shared memory and also what we call the Cray supercomputing line, which is a new thing we're developing this particular year. We have a set of HPC and AI platforms that house accelerators, so that's part of our portfolio as well. Some mainstream HPC and AI platforms, this is the Apollo 2000, for example. And finally, we have the converged edge products, such as the EdgeLine 8000, that's specifically for edge computing, so inference and computing that's happening on the edge. So underneath of all these platforms, we have storage platforms as well. Obviously storage is important, and we have an integrated approach around storage. And of course, we have a very extensive software portfolio for both HPC and AI. So one of the gems we got from the Cray acquisition was their software stack. And finally, at the end of this, it's all available as a service. So we have a product called GreenLake, which allows us to deliver everything we have in the portfolio as a service, as opposed to a more traditional type of CapEx purchase. So let's dive into some of these product lines in more detail. So first off, the Cray EX is our top supercomputer. This is the one that will be part of the 3 exascale machines that we will be delivering over the next couple years. And we've had great success with this platform. So we've got major installations around the world at weather sites and national centers, in defense organizations, as well as in some commercial customers. So we'll have some announcements around some commercial customers over the next couple of months or so. And so in this case, this houses up to 512 processors in a rack in 64 blade configurations. It also supports a variety of different types of processors and accelerators, and it's also future-proofed. So it's able to accommodate the future roadmap for a lot of these processors and accelerators that become more powerful but more power hungry and hot as we go forward. It has 100% direct liquid cooling, so it's room neutral, so it does not expel additional heat into the data center. So because of the water cooling takes away all the heat, there's not a need for additional cooling from that standpoint. And it will scale to hundreds of cabinets. So some of our exascale type of installations will be, in some cases, close to 200 cabinets with this particular platform. So next we have what we call Cray supercomputers. And so the Cray supercomputers will take a lot of our general purpose servers, whether they're the Apollo line or the ProLiant line, with a variety of other types of solutions together and integrate it with some of the Cray software, with Slingshot as an interconnect as well, to bring in that capable interconnect, which we'll talk about a little bit more in a while here. And of course, again, brings in a lot of the Cray software. And so just as a comparison point, you'll see on the left-hand side of the slide here, this is our Cray EX. So again, pretty specialized cabinetry from that standpoint. So in order to get that density of 512 processors per rack, specialized cabinets as well as integrated switchblades as well from that standpoint. And so again, it's 100% direct liquid cooled platform. Then you have the Cray standard 19-inch cabinet. This is where we have the Cray supercomputers in. So that means you can still have a Cray supercomputer that can fit in a 19-inch rack and bring in a variety of other type of computing elements, different types of networking capability and so forth. And again, both of these can scale to very large systems. So whether you're the Cray EX platform or you're the more standard rack platform. And here are the 3 exascale machines that we'll be delivering over the next 3 years. In the center is Frontier. Now this is on the floor today. This is Dr. Al Geist was talking this morning about Frontier and the work that they hope at Oak Ridge National Labs that they will do with Frontier. This will probably end up as about a 1.5 exaflop in terms of its capability, and it's based around AMD CPUs and GPUs. Also has a very large storage component, 700 petabytes of storage that's available, and able to accommodate both an HPC as well as an AI workload. And so again, that's being delivered. It was actually delivered last year. We're in the process of integrating that, bringing that up. On the left-hand side, you see Aurora, which is the next platform that we'll deliver, and this will be based upon Intel technology. And so it will be at Argonne National Lab, which is in the Chicago area of the United States. And then finally on the right-hand side, and this will come in the, probably the starting install in the 23 timeframe. And so that's called El Capitan, and that will be at Lawrence Livermore Lab in Livermore, California. And that again is an AMD CPU and GPU combination. One installation that we have here in Asia Pacific that has been in operation for a while is at Palsy, in Western Australia, in Perth, Western Australia. This is meant to cover a variety of different research efforts that are being done in Australia, from seismic processing through climate research, through fisheries research, and these sorts of things as well. And it's a combination of the Cray EX supercomputer that we talked about, plus the Cray cluster store compute, and it's a 16 rack system. So it's not at all a small system. It's a large system from that standpoint, and combines both the high density racks and the more standard racks. So you can have a system that combines different elements together depending upon what your requirements are. And this has about 14 petabytes of storage, which is a significant amount of storage as well. And again, the Slingshot interconnect pulling all the different elements together. So great success here in Asia Pac at the Palsy Center. One of the offerings we have is the Superdome Flex, and the Superdome Flex actually allows for processing of large memory type applications. So in cases where a model is very large and there's an advantage to bringing all that data into a single system image. So this is just running one instance of the operating system, and being able to manage that data in a very monolithic way, which typically increases the I think I pushed the button here. I don't know. That's right. Yeah. And so it's actually, if you're familiar with the SGI UV product, this was the next generation of the UV product that's been brought on board after the SGI acquisition. And so it does scale very well. So you can start with a single chassis, which is called the Superdome 280. And then start to scale up until you move into a Superdome Flex type of configuration. And again, it cables up, it's very highly integrated and also very efficient. Again, as I mentioned, this is shared memory HPC. So we're generally used to a lot of cluster-based HPC, but again, there are applications that benefit from the fact of having all the memory in the single system image at one time. So let's talk a little bit about some of our accelerated type mainstream products. One of those is the Apollo 6500 Gen 10, followed by the Gen 10 Plus, which is Gen 10 is prior generation, Gen 10 Plus is the latest generation. And so first off, we have a software experience that we built around this particular platform, allowing a variety of different both management and runtime and development type of environment. We also run a variety of different operating systems here. Not limited, we can run Red Hat, we can run Ubuntu, Windows, VMware, as well as SUSE. So a lot of flexibility in this particular system. There's also a variety of different choices in terms of both capabilities. It can use a NumaLink connected type NVIDIA board, but at the same time it does have PCIe slots if you want to use the PCI cards, whether they're FPGA cards, whether they're AMD GPUs and so forth. And also a variety of different accelerator type topologies to meet your particular needs. And it also has a variety of different types of processors, so Intel Cascade Lake, and now also the AMD EPYC, which is available in the Gen 10 Plus platform. And again, a variety of different accelerators available from the NVIDIA Tesla through the Intel Nirvana processors, as well as the AMD Instinct as well. So we call this the AI supercomputer because this is what a lot of customers use in terms of their AI workloads. And so, a little bit more detail from the 6500. So again, this is a use case for a lot of AI type workloads, whether you're autonomous vehicles from that standpoint, pattern matching for fraud detection, things like monitoring, so gathering a lot of data and being able to analyze it very quickly. So we have a customer doing that for oil drilling rigs to be able to gather lots of data and make decisions around that. And also being used for drug discovery as well. So that's another use of the platform. Again, the customer benefits here is a lot of flexibility, a lot of different types of options from interconnect through processor options, software options, operating system options, and so forth. So that's one of the popularity of this particular platform. And finally, an integrated software and hardware package as well that we deliver to the customer. Let's talk a little bit about, so we've gone from very high-end supercomputing to our AI mainstream platforms, and now to our more conventional compute type platforms. And the star of that platform is actually the Apollo 2000. And so this is really our most popular platform. So we literally sell thousands of these on a regular basis. So it's a 4 nodes in a 2U, and these are 2 socket nodes. So both Intel is available in the platform, whether previous generation was Cascade Lake, current generation is Ice Lake, and also AMD processors, whether they're prior Rome or also moving into Milan as well from that standpoint. There's a lot of expanded power capabilities over our prior generation. So we've got 3 different power supplies that you can choose depending upon the particular configuration you have and whether you want to have power redundancy in case you lose one of the processors. And there's a number of different flexibility in terms of scale out building blocks. So different trays that you can use, either 1 or 2U trays, allowing both GPUs, storage, so adding additional storage capability as well. And you can basically right size the platform based upon your particular application. And it has very comprehensive server security and management. So based upon our ILO and our silicon root of trust types of capabilities, and a lot of flexibility in terms of interconnect, being able to can be connected up via Slingshot, via InfiniBand, and so forth. So again, some of the high points of the Apollo 2000 Gen 10 Plus, high density but low TCO. So we've got again four server nodes in a 2U. That's about 2x the density of more general purpose type platforms. Again, a lot of customization options depending upon the trays and the processors and so forth that you happen to pick. A comprehensive software stack from our HPE Cluster Manager, as well as the Cray programming environment, so that's available as well. And then finally, the HPE message passing interface for accelerated performance, whether you're using Slingshot or InfiniBand as well. So again, the Workhouse HPC platform for a lot of customers. Let's talk a little bit about our Edgeline 8000. So this was the higher end of our Edgeline product. So this is the line that we're continuing to go forward. We've had a fair amount of success with this platform in both defense applications and in telco applications. So as a compute node at the base of a telco, a wireless type installation sort of thing, wireless antenna, there we go. And so this is based upon the Moonshot cartridges, so very, very dense type cartridges. We have the E910 1U blade, which is based upon the Cascade Lake processor. And so a lot of dense compute that's available. And then we also have a 5U chassis as well as a 2U chassis in this particular model. And then finally, our storage products, the ClusterStor E1000 is our Lustre-based product. So, and I'll have a cheat sheet in a little bit to show you where you should use ClusterStor versus where you should use PFSS. Again, this is the storage product of choice for a lot of our larger type installations. It also integrates with DMF, which is our data management framework for managing a multi-tier type data environment. The PFSS, or the Parallel File System Storage, was introduced about 9 months ago. It's based upon spectrum scale as opposed to Lustre. And so a lot of customers who already have spectrum scale or want the wider feature set of spectrum scale can use this particular platform. It actually exists on some of our standard HPE ProLiant type servers from a hardware perspective, but then we also integrate the software in that as well. Here's a quick cheat sheet. Again, if you're a large or extra large type use, so either hundreds to thousands of compute nodes and a petabyte or more of storage, then the ClusterStor is probably the right storage for you. However, if you're smaller, you've got a few nodes, or smaller type, more like terabyte size, you should go with the PFSS from that standpoint. And again, there's Lustre versus IBM Spectrum Scale in terms of the file system. And so, we've done a lot of work, so we integrate these storage products with our other storage products, so that makes sure they all work well together, so that's something that we do ourselves. So that's where we get also some great performance and great efficiency in these systems. And our software portfolio, I won't go through every one of the offerings here, but just to give you an example of all the different, we have a lot of IP that we work on ourselves. So we've got hundreds of engineers working on system management, runtime, as well as the development environment. We have a lot of integrated third-party options too, probably just about every third-party option you can imagine, from load levelers to development environments to runtime environments to management environments as well. And then finally, all these platforms are ready for the exascale era. So as we deploy those 3 exascale machines I mentioned before, we'll be having new software, new compute with a variety of different processors, new storage, as well as our Slingshot, which is our high-speed interconnect, that will give the type of performance, quality of service, and congestion management control that's available. And we have a complete services offering as well for all these platforms. And then finally, all of this is available through GreenLake, which is our as-a-service type offering. So if you want to have an OpEx-based solution and be able to grow your solution flexibly, GreenLake is probably one of the options for you as opposed to more of a standard CapEx purchase. And we have a variety of different services for deployment and optimization of GreenLake. So, again, if you want to get faster time to market, if you want to have OpEx savings and more flexibility of compute and saving of IT resources, because in some cases we'll manage the system for you. So you can bring it in your data center and have that security, but at the same time have us manage it. A little bit more detail in terms of what we're able to do here, so I covered this already. And so then, here's our summary. We've got high-end platforms, mid-range platforms. We've got high shared memory platforms as well. We've got a variety of different types of software, whether your more traditional type software or our Cray system management software. And also a complete development environment. Also our fabrics, whether they're HPE Slingshot or more standard IB or Ethernet. And finally, storage capabilities across both systems. So again, as we move into the exascale area, this is from Rick Stevens, who is the director of Argonne National Lab that's doing the Aurora system. So these systems are going to be large systems and have that kind of capability. So they're simply the biggest, baddest machines we can build out of the conventional technology that's available. So, again, this is our portfolio. I thank you for your time today and hope you enjoy the rest of ForCAST and the rest of the show. Thank you.
Hang on are there any questions for Bill? No, it's clear. Thank you. Okay, thanks, Bill. That was very, very useful. We're going to have now a virtual presentation. The next speaker is Hoang Pan. He comes in to HPE from a recent acquisition of a company called Determine AI. Determine AI is a software company, and what basically it is, it's a platform to do or scale up your GPU development, and it's sort of GPUs agnostic. You can have a variety of or mixed GPUs, and you can still use the same platform, which means you don't have kind of lock into a certain type of software. This software will let you play with anything. So without taking more time, I'll let Hoang to sort of explain everything about this platform. Please welcome Hoang. Thank you.
And all right, see if I can advance this slide here. All right, Raj, just double checking. Can you still hear me okay?
Fine.
I believe we're sharing the presenter view. Are we switching that over, or should I just go with this?
We can see your slides, so.
Okay. All right, so just to get started, again, my name is Mike. Thanks for taking the time to learn more about the HPE Cray AI development environment. In terms of the content for today's conversation, I wanted to talk a little bit more about the HPE Cray AI development environment and how that helps with machine learning and, in particular, deep learning workflows. So you've probably heard of all the different innovative things that are happening with deep learning and all of the use cases that it's driving. So for context, if we're referring to machine learning as structured data for more traditional statistical machine learning algorithms, then deep learning is on the unstructured side, working with neural networks. So for deep learning, you see use cases like autonomous vehicles, so being able to detect pedestrians and other objects on the road. You might look at drug discovery, so identifying how compounds interact with cell microscopy and other areas in biology, and then also potentially in defense. So these are just a few different use cases that you may have heard that have been enabled by deep learning. But if you really think about it, all of these use cases are powered by deep learning models. So these models need to be developed and created a certain way. So if we think about the overall process for how deep learning development works, you can think of it very similar to statistical machine learning in that you have three main components. You have an initial data collection and ETL data storage phase. You have the development phase, in which case this is where your actual model development is happening in the center. And then afterward, you have a deployment phase where you're deploying that particular model to an endpoint. So throughout all these phases, the middle part, the part where you're actually doing model development and training, typically looks something like taking existing model code or writing your own, testing a sample data set, optimizing that model based on your results, scaling that training out potentially to hundreds of GPUs or other accelerators, validating those results, and then going back and then making your updates. And that is a very cyclical event. And typically within that process, you'll see a few different capabilities that are required by these model developers. So the first is typically the ability to use the most popular machine learning frameworks like TensorFlow, PyTorch, Keras. Then within the development phase, you're going to do a lot of experimentation, having a system that's going to allow you to experiment with different models and test out different capabilities. During that experimentation phase, you'll be looking at optimizing that model, either through what's called hyperparameter search, where you're looking through a large number of different models that may result in better accuracy or other metrics relative to your data set. Other options include looking at scaling out your training, like I mentioned before. So using more than one accelerator, potentially hundreds, in order to train your model more quickly, and then collaborating with others on your team. And then on top of all of this, you're looking to have the ability to track a lot of different experiments and being able to ensure that your experiments are then reproducible at a later point in time. And then below that software layer, you're looking at using different accelerators. They potentially could be heterogeneous, even if it's different accelerators from the same vendor, maybe different vendors. And all of these things need to work together in order to accelerate and scale out that model development phase. And that's not even considering whether you're running on-premise or in the cloud. So all of these things are capabilities that these deep learning model developers are looking for. But it turns out that from what we've seen in industry, this is actually a very hard problem. And it's hard when it actually scales out. So when you have a much smaller team or you're working on a much smaller project, usually these capabilities are very easy to come by because you can just use open source tools. But once you scale out to hundreds of GPUs on a cluster, maybe a much larger team, these become much more difficult to manage. And because of that, you see some issues with the different types of frameworks that are being used, the size of the team. How do you share those resources on a cluster in order to train your models much more quickly and efficiently? And then what do you use to manage all of these resources and schedule and make sure everything is running efficiently on your system? And from the point of view of developing a solution, there are a few options, right? A lot of the largest tech companies have invested huge amounts of money into building out a team and building out infrastructure that satisfies these requirements. So they've built their own software. Think of the Googles and the Facebook or Metas of the world that have invested a lot in ensuring that they have this type of infrastructure on the software side. But for a lot of companies, that doesn't really make a lot of sense in terms of the return on investment. So what instead they're looking for is a solution that satisfies all of these requirements, but is something that they can purchase or maybe test out, use as part of an open source tool. And this is exactly what we're looking at providing with the HPE Cray AI development environment. So if this looks familiar to the earlier slide, it is. So the main focus here is on the model development and training phase. And this is where we add in the capabilities of managing heterogeneous accelerators on your cluster, being able to offer very simple distributed training, experiment tracking as you're doing your model development, as well as advanced capabilities like hyperparameter search, neural architecture search, and visualizations that are required in this development phase. And this system integrates with incoming data source. So we're agnostic to where your data is coming from, and it outputs a model that can be used downstream in various applications. It could be an API endpoint. It could be in a vehicle for autonomous driving. So we're agnostic to those components. We focus very heavily on the model training side and accelerating that mode. So typically what we'd like to do here is run a quick demo live, but just given the quality of the video from a remote session, what we'll do is I'll play a video here that will show what the capabilities look like for the development environment. So I'll go ahead and start the video. There'll be audio coming from the video, but I'll chime in if there's any specific information that I think is relevant to our discussion here. In Determined, the two main files that you'll need in order to train a model are a configuration file and a model directory. The model directory, as named, will contain the model itself as well as any dependencies that are required in order to run the model. And the configuration file will include configurations that will tell Determined what you'd like to do with that model. Let's go ahead and launch this, and we can take a look at the results on the Determined cluster. We're currently using the CLI in order to launch this, but we can also use the Determined Python client if you'd like to write this in Python as well. Once executed, we see that experiment 208 has been created. We'll go from this Jupyter notebook over to the Determined cluster. And as you can see in the Determined cluster, our experiment has started and is currently active. Let me first take a quick step back and talk about the Determined UI. The Determined UI is designed in order for model developers to be able to track and monitor their models as it's being trained. So it allows an easy interface for model developers to see their training, as well as take a look at the entire cluster as a whole. Now, a couple of areas where this could be useful. In terms of the model training itself, you can see that I can see a few experiments being executed currently, but I can also filter by additional users that are currently on the cluster. This is helpful for large teams that work on multiple different models but want to share resources. Pulling resources together allows your cluster to be much more effective and allows the cluster to be much better utilized. As a model developer, I can also take a look at the cluster itself and see the resources that are currently available to me. In this case, this particular cluster is deployed in the cloud, but you can also deploy this on-prem and it'll work just the same. Right now, I have 8 GPUs available, and 2 of those 8 GPUs are currently being used. Going back to the experiment itself, let's go ahead and click into the experiment that we just launched. In this experiment, we can see that Determined is tracking the model training. You can see key information related to the training time, validation time, as well as checkpointing time, and then also see the first set of batches and the resulting validation average IOU, which is the metric that we are optimizing for this particular model training. You'll notice that Determined automatically takes checkpoints for the model training itself. The frequency of these checkpoints can be configured by the user, but the idea is that the user does not need to write additional scaffolding code in order to take checkpoints intermittently throughout training. This is beneficial because as this model is training, you may encounter some issues with the hardware itself, and you may need to restart your experiments based on some of those issues. With automated checkpointing, you don't have to worry about having to restart your model after it's been training for days. You'll know that you can always restart from the last checkpoint taken, which should be very close to where any issues may have occurred. In addition to automatically checkpointing for fault tolerance, the automatic checkpointing allows you to pause and resume models as needed. So for example, if you were training a model and you wanted to pause it in order to free up resources for another model, you can go ahead and pause it here and then resume it at another point in time. On the back end, Determined restores and saves your checkpoints in order to allow you to do that easily. Looking at additional information that Determined keeps, let's look at the configuration for the experiment itself. Determined automatically keeps experiment configuration and metadata for every single experiment that's run on the platform. Here you can see information like the data that's being used. You can see the image that the model is being trained in and the associated environment that's in that image, as well as hyperparameters that may be used during the model training itself. Determined even keeps things like the random seed in order to properly reproduce the model at a later point in time. All of this is taken automatically, so the user, again, does not need to worry about writing additional scaffolding code in order to save all this information. It's available within the Determined database as soon as this experiment is run and can be used or queried against at a later point in time. Another nice feature with Determined when you're running a model training is that we include a built-in profiler, so you can look at system metrics as you're training. Common system metrics like network, GPU utilization, memory are all logged here so that a model developer can see how their model is performing throughout the training itself, and potential areas to optimize. Determine also includes timings for specific functions as part of the model training. For example, for this PyTorch training, you have different sections involved with training the batches, for reducing the metrics, and other areas that you may be interested in seeing how long it's taking throughout the model training. And then, of course, Determine stores all of the logs associated with the training itself, so that you can always go back and take a look, either debugging or just to see how the training did, and anything else that you're producing in the logs will be stored here as well. Finally, if you take a look at the model itself, we can see that we've logged a few different sets of validation metrics here, and Determined will natively graph these for the model developer. In addition to this native graphing and visualization, developers can also use native TensorBoard. So by writing your TF events files out to a specific model directory, Determined can run the TensorBoard natively, and you can take a look at what the exported TF events files look like and monitor your model that way. All right, great. So we've completed training for this single GPU model. Now, what if we wanted to introspect the model a little bit? We want to pull the best checkpoint from that training and then go ahead and take a look at how that particular experiment performs against a test image. Let's say this image of some pedestrians walking on the sidewalk. Well, we can use the Determine client to pull the best checkpoint for any given experiment. Since we started experiment 208, let's go ahead and set 208 here. We can run the checkpoint pull. In this case, we're pulling the top checkpoint from this particular experiment ID. And then after this checkpoint is pulled, we can go ahead and run our predict function against this image. Looking at the result, we can see that the model itself has predicted and seen one person in this image, which is a great start. But it is not really the best performing model at this point. What we'd like to do is train this model further, but on one GPU, it may be a little bit slow. Instead, what we can do is distribute this across multiple GPUs and train on Determine that way. Typically, in order to distribute across multiple GPUs, there's a host of things that a model developer would have to worry about. Things to consider being provisioning the hardware itself, installing the right software on the back end on each machine, making sure that the networking is set up correctly so the machines can communicate, ensuring that there is automatic checkpointing, ensuring that there's a way to easily shard data across the different machines, as well as many other things to consider. Typically, model developers would prefer not to have to work on that part of the training and instead focus on experimenting with the model itself. With Determined, we make distributed training very easy. All a model developer would need to do is update their configuration file. In the configuration file, we have a single line called slots per trial. A slot, in this case, is a GPU. Instead of 1, which is the default value, a model developer can change this to any number. In this case, we can set 4, but you can set this to 64 or an even larger number, depending on how quickly you'd like to train across your data set. Once that's done, you can launch the experiment the exact same way, and Determine will take care of the rest. We've created experiment 209, which is a distributed training experiment across 4 GPUs. On the back end, Determine is taking in that experiment code, sharding the data across 4 different GPUs, and then training it in parallel. All of this is done automatically, and the user no longer needs to worry about anything else. If we take a look at the experiment itself, we can see that we have a new experiment that started here. As part of the configuration file, we've labeled this as 4 GPUs for future reference, so you can go ahead and filter this. All right, so I'll go ahead and pause there just given time, but I wanted to just make sure we highlighted some of the key things that were shown in that demo. So the main thing is that in training a single GPU on a cluster, typically that's not the hard part. The hard part is all of the additional capabilities that I'd mentioned, the experiment tracking, managing the cluster, et cetera. And that's done all completely with the HPE Creative Development Environment platform. And the transition from a single GPU to multiple GPUs, as you saw, is as easy as changing a single configuration. And I think that's one of the key things to consider when thinking about scaling, whether you're in the cloud or at the core, is how easy is it for your users, your model developers, to scale out their experiments and then be able to train with all of those resources that you have on a system that can make that much, much more efficient. So I wanted to make sure that we were able to go through that part of it. And just to wrap things up, let me just move to the next slide. Yeah, just to wrap things up, a couple points here in terms of the AI development environment. So one, the development environment is built off of the Determined AI platform, which is an open source core. And of course, if you're interested in testing this out, you can definitely go to our GitHub and take a look and check that out and install it on your own, either local machine, a laptop, or maybe a portion of your cluster to test out the actual capabilities. But the AI development environment is the enterprise offering, which has additional security and enterprise features that a lot of our organizations that are looking for those types of capabilities are looking for. But in terms of the main ideas from the overview so far, I wanted to just mention top 3 things here. So one, the platform is designed to allow you to train on core or cloud in order to allow that adaptability and flexibility, as well as the potential cost savings. We're seeing a lot of organizations that are using a huge amount of GPUs move from cloud to core, or maybe cloud to different cloud. And that portability is something that is innate in the platform and is really helpful for a lot of these organizations. So I think that's something that is very useful to have, especially in a platform that you're using for potentially AI and ML training, as well as potentially HPC. The other is the ability to distribute training and provide those advanced capabilities that we just saw. So being able to allow your users and your model developers to leverage those capabilities is essential, ensuring that they can train their models quickly and get to better models so you can produce the correct business objectives that you're looking for within your deep learning project. And then finally, as one of the additional elements of that productivity is being able to collaborate with teammates and other colleagues that are working on potentially similar models. So you saw the ability to reproduce experiments and be able to continue training and share some of those models across the same platform. That's something that we also enable and ensure that the team is as productive as possible. All right, so hopefully that was helpful and gave some insight into the AI development environment. So I'll go ahead and conclude here and hand it over for any additional questions.
Thank you. Wow, very, very nice. Any questions from anyone? Actually, I noticed, Huang, that in Singapore, most of the AI workload we see is typically single GPU, and we haven't seen a lot of multi-GPU user base. But maybe the platform is so easy that you just showed. I was just itching that maybe I can try. So I think this is really fantastic. Thank you so much for this great presentation. And with that, thank you. And we'll move to the next speaker in line. He's one of my ex-colleague, and kind of continuing, because obviously he's from Cray. So he is the master of Slingshot. He's the product manager and also responsible for business development for the Slingshot product. Jesse has a lot of experience and currently very hands-on. So you will see in his presentation that he's going to explain that how HPE Slingshot is the interconnect of the future. Thank you.
Thanks, Raj. Is everything coming through okay? Just make sure.
Yes, if you click, yep.
Okay, there, now it's working. All right. So thank you, Raj. Yeah, so I'm a Slingshot product management. I'm joining you today from the US. I'm looking forward to joining you face-to-face as soon as I can. And I'm going to give you an overview of the Slingshot Interconnect. And so just to start with, there are quite a lot of trends driving high-performance networks, and I don't think I need to explain these to you. You guys live this every day, and you're probably exchanging these thoughts with colleagues at the conference. And some of the things we hear is the growth of AI in addition to traditional simulation, all sorts of new data coming into the high performance computing resource, including streaming from sensors and instruments, and lots of new users who want to run different types of applications than you might be familiar with. And all of these are on top of the traditional HPC challenges of needing to do more with less, wanting better price performance, dealing with heterogeneous computing. So we've developed HPE Slingshot to really address these emerging challenges and give you no compromise performance for these data-intensive applications. And I like to think about it as arming you to be ready to handle whatever might be thrown at you. So in a nutshell, one of the most exciting and interesting things about Slingshot is we're bringing together Ethernet, which is the standard for connectivity in the data center, with the high-performance interconnect. Cray's built many generations of high-performance interconnects. They have the special capabilities to deal with low-latency applications, be efficient for small and large payloads, and have hardware acceleration for the kinds of applications that we run that are on MPI. And so with some of our unique and powerful innovations in Slingshot that I'll talk about today, we overcome the barriers that up until now have prevented people from using Ethernet for high performance computing, and doing it in a way that's efficient, whether you're running at exascale or a single rack. Now, Bill showed a number of the design wins that we have with Slingshot. Here I've added some of the top 500 results from the recent fall supercomputing. There's a lot of things I like to highlight. Bill highlighted some of them. These are wins across industries. These are wins across geographies. But the one that I think is the most interesting from a Slingshot perspective is these are across architectures. There's something like 5 or 6 GPUs here, 4 or 5 CPUs here from Intel, AMD, and NVIDIA. And this is a particular concern for our customers in the interconnect space, that they want to make sure that they can still have a high performance interconnect that will give them the choice for the best of breed processing. And right now, Slingshot is the best choice out there for that. So what does Slingshot give you? Well, in a nutshell, performance, efficiency, and high service levels. You know, we've always been known for performance at Cray. I like to describe it that we take it to a new level with Slingshot, where we're talking about delivered performance under load with low uniform latency and high bandwidth, meaning in a real topology with real congestive applications running, you will get performance. But it's not just performance at any cost, but performance has to come with efficiency. You guys all know it's about price performance. And the architecture of Slingshot is designed for efficiency. That's why we have so many design wins, as you saw in the previous slide. For an example, I'll show you how our fine-grained adaptive routing lets you consume the bandwidth that you've bought. And that means you don't have to over-provision bandwidth to overcome congestion, as is common in the industry. Also, things like fewer optical cables through some of the intelligence in our architecture. As Bill described, and this is particularly true with Slingshot, we take the solutions approach, right? We have software that takes advantage of Slingshot, management software that knows how to take advantage of Slingshot, and support to help you answer those system level questions like, why is my job running slow? And not force you to figure it out yourself between the different components. And of course, it's Ethernet. And on the right, you see some of the key technologies that I'm going to touch on during the talk on how we're able to accomplish all of this. So it starts with silicon. So while we're Ethernet, it is our own silicon, in particular, our own switch silicon. You cannot do HPC on Ethernet with merchant market switches. They trade off bandwidth for latency. Slingshot is optimized to do both together. Our switch is right at the leading edge of capability with 64 ports at 200 gigs. That's 25 terabits of bandwidth. Each port is 100 or 200 gigs. So it's right at the leading edge of what you can do. And it's that switch that in particular overcomes those issues for running Ethernet at supercomputing scale. Later in the presentation, I'll talk about our NIC as well. This is called Cassini, and this is what's going to be rolling out in that frontier system first. Let me start with an overview of our portfolio. So again, starts with our silicon. From the switch perspective, we have 2 form factors. That direct liquid cooled Cray supercomputer form factor that Bill showed, that the switch is a blade. and standard top-of-rack infrastructure in an air-cooled rack. From a NIC perspective, we work with both qualified industry standard NICs, such as the Connect X5, which is what we use today. And all of those top 500 results that I showed you were with the Connect X5 NIC, right? So again, it just proves that with our switches, we overcome the barriers to making Ethernet-based HPC run at scale. But we also have our HPE Cassini NIC, which is just now rolling out. And this is highly optimized for supercomputing class performance. And I'll give you some examples of some of the capabilities in there later about why that is. And of course, we round that out with the cables that you need to make all this work together and the solutions that I talked about earlier. Just a quick glance, you'll see more of this, I think, later from Steve, but how this works in a Cray EX supercomputer. It's a very cool architecture if you haven't seen it. The compute blades go into from the front, the switch blades go in from the back. They mate, so it's a very clean implementation where there's no cables between the compute nodes and the switches. And everything is 100% direct liquid cooled. So you can see on the graphic on the top, there's the cooling plate on the switch blade. On the bottom, you see the compute blade. Those green boards is the NIC. Those share the cooling plate with the CPU. It's a very nice solution. And what's particularly exciting about this is this supercomputer cabinet, Bill gave you all the specs, and it has 8 chassis, each with 8 blades, and each of those blades with 2 or 4 nodes. So it's a pretty big, hefty system. We have a version of this coming out for smaller scale systems that I think Steve's going to talk about later. And that gives you an opportunity to consume this direct liquid cooled slingshot in a much smaller entry point and much smaller chunks of scale. But of course, it's not just for supercomputers. We now have Slingshot available in systems that run Red Hat, and we'll hear more about that from one of our customers later today. And you can manage this with our standard cluster manager, the HPE Performance Cluster Manager product. So one of the exciting things is we've taken it out of the supercomputers and we're bringing it to the market, to the cluster market as a whole, and make Cray supercomputing class performance accessible at much lower price points. And I have a couple of universities, for example, running Slingshot in systems of a couple of hundred compute nodes. So very exciting that we've done that. Now I want to shift and get into the technology and explain a little more about how Slingshot works. Because while it looks, that top of rack system that I just showed you looks like a standard Ethernet switch, it really operates very differently. The analogy that I like to use is that you should think about this network of Slingshot switches as a giant director class switch, a giant core switch, except ours scales up to tens of thousands of ports, for example, with one of those exascale systems. And so like in this picture, that gray box, think about that as that core switch. Now you configure those ports either as a fabric port that connects to another Slingshot switch, or as an edge port that talks to standard Ethernet devices like that Connect X5 NIC. And it's on those, they're both running Ethernet, but it's on those fabric links in particular between the switches where we've done a lot of these creative innovations to overcome the barriers for using Ethernet. We have optimized protocols at the wire that are more efficient and more resilient than standard Ethernet packets. And we have optimized fabric protocols for routing and congestion control. Ethernet networks are not very good for HPC because when they drop packets, it adds a lot of latency. All of those features prevent us from having to do that and help us achieve the kind of performance that you saw for those top 500 runs. Now, like that giant director switch, there's a management blade. In this case, the management blade is a separate server complex, and it connects to all the switches with an out-of-band management network. Now, one of the reasons people want Ethernet is to be able to connect to the rest of the data center and connect to the rest of their data. And the way we do that with Slingshot is with an edge router, usually something like an Aruba switch from HPE or Aruba 8325, or some qualified third-party switches from Arista, Cisco, and Juniper. And you can build a wide lag from any Slingshot switch into these edge routers and have a very high bandwidth connection to your storage that might live outside of the fabric. Now, one of the innovations that helps us with efficiency is our Dragonfly topology. And just since I'm going to kind of come back to this cartoon picture of the topology later, just to explain it really quickly. Each of those black circles represents a switch. So those connect to, let's say, 16 compute endpoints. In Dragonfly, you arrange those switches in a group where they're all connected to each other. That's one of those circles. And then each of those groups is connected to all the other groups. So you could think of one of those supercomputing cabinets as a group, or 2 racks of Apollo 2000 as a group. And there's a wide range of group sizes. The beauty of this is only the cables that connect the groups together are typically optical cables. So what that means is a tremendous amount of efficiency and reliability versus other topologies. We use about half the optical cables of a fat tree for a given global bandwidth, which saves a lot of cost. And the whole topology is much more forgiving, and it scales really well. You can reach on any of those exascale systems with tens of thousands of endpoints. You never need more than 3 switch-to-switch hops to go from one node to another. Now, that's not a simple thing to do. Part of that is because we've perfected this over several generations, and part of that is because of the technology that I'm going to talk with you more about, our fine-grained adaptive routing and our automatic congestion control. So now I want to shift into how we deliver performance with Slingshot. And the name of the game, as many of you know, is achieving great performance on tightly coupled codes. Is you're really trying to minimize the communications time and maximize the computation, right? And in particular on that communication, it's not just the average packet, it's really that last packet, because with these tightly coupled codes, you're waiting for that last packet to come in before you can proceed to the next step. So as a software developer, what you really want is like infinite bandwidth and 0 latency, or as close to the theoretical maximum as you can get. And that's what we try to do with Slingshot, is deliver you that, but in real use, not in sort of theoretical benchmarks, but in real use, like with other applications running on the system and in a real topology, and where you have real congestion. Let me talk about a couple of the ways that we do that. The first is our fine-grained adaptive routing. Now, adaptive routing is kind of a generic term. It just means you're load balancing across the links on the system. But what we do is fine-grained adaptive routing. And what that means is that, normally you're sending your packets on the shortest path. But what if that path gets congested? You got a lot more traffic going over it, it gets congested. Well, what we can do is even as granularly as on a packet by packet basis, we can take advantage of other paths in the network. Basically, let you actually achieve value out of all the bandwidth you've bought by making sure you can utilize it. But not all traffic can be unordered. Sometimes traffic needs to be ordered. Ethernet traffic needs to be ordered. Well, here too, we can do a fine-grained adaptive routing. We detect when the flow is completed from the network, and the next time a flow comes in, we can reroute it. If it's a long-lived flow, we can pause it and have it take another path if the original path was congested. Why do we do that? Well, there's a lot of bandwidth, a lot of benefits to that. The primary one is you can get the full use of the bandwidth of your topology in real practice, right? And we can do that both for the ordered flows, but it's almost as good with those ordered flows as it is with those unordered flows when we're rerouting on a packet by packet basis. This is also one of those things that lets us do that Dragonfly topology and save all the cost of those optical cables. And just as an example of what this gets you, here's a benchmark that looking at the traffic across those global links. The x-axis, each of those bars is one of the global links. And you can see that you're getting very close to the theoretical maximum on the global link with this all-to-all application because of the effectiveness of the adaptive routing. Right, so that explained one of the ways that we overcome congestion on a link. What about congestion on an endpoint, right? Now, here's where that tail latency is so important, because that's what drives performance. But what happens is if you're receiving messages faster, because there's an incast problem, that faster than you can take them off of the network, well, that creates pressure back through the network for all the traffic going through the switches to that node. And that's what leads to high tail latency. And what Slingshot does is detect that in hardware. and put back pressure very quickly onto the sending source to cut off that congestion and keep that tail latency from increasing. And you can see an illustration of how that works in practice with the two charts on the bottom. The left one is a chart of our GPCnet benchmark, which is a measure of latency, but latency in a real system, not theoretical measures of latency from like one switch port to another switch port, or ping pong latency with nothing else running. This is in a real topology. And you can see the top set of bars of the Slingshot interconnect and in the lower purple, and the others are InfiniBand and our previous generation of Aries interconnect. You can see that there's an average latency in the top set of bars, but the tail latency, this is like the 99th percent packet, is quite a bit slower, right? There's an exponential scale on this. But where you really see this is on the lowest bar, where I'm looking at that tail latency with other things running on the fabric that are creating congestion. And you can see that systems without congestion management schemes, or with the industry normal congestion management schemes like ECN, have a huge hit to tail latency. But because ours reacts quickly, right, which is important for HPC applications where these flows are very short-lived, we can nip it in the bud. And you'll see that the Slingshot latency is very consistent whether there's congestion or not. Now, and there's orders of magnitude impact on the tail latency. What does that mean from an application performance standpoint? Well, you can see that in the study on the right. This is with GROMACS, which is a molecular dynamics code. And this is comparing our previous generation to Slingshot. The orange is previous, the blue is Slingshot. You'll see that the Slingshot performance is consistent. Even with all but the first bar, I'm adding congestors running on the network. The first set of bars is running exclusive. You'll see the performance on the Aries interconnect jumps around quite a bit and can fall by close to half because of this impact to tail latency. And this is similar to what you would experience on any system that has the delays to tail latency, like you see on the chart on the left. Now, we do also have quality of service capabilities. All of the adaptive routing and the automated congestion control work automatically. But if you want to allocate bandwidth and prescribe traffic classes to have certain policies, we have those capabilities as well. So let me shift gears and talk a little bit about the HPE Slingshot NIC, right? So again, I showed you that today we're running with those CX5 NICs, and we're rolling this out into the exascale systems. So this is with our own silicon. It's a PCIe Gen 4 200 gig NIC. And again, it uses standard Ethernet, so it can run standard IP traffic. But here we use our native RDMA transport and our native RDMA offload. So we're not using Rocky for this. We're using our own native RDMA. And the reason we do that is to get very high performance, very high sustained bandwidth, very high sustained message rates, very high scalability, and efficiency for small transfers, which are particularly important for certain classes of applications. For example, the intelligence community uses small transfers and SHMEM and PGAS type of workloads very extensively. Right, so let me go back to that picture of how you want to optimize performance, right? Again, you want to maximize compute and minimize communications. And let's zoom in on that communications piece. And you'll see there's part of it that happens on the host and part of it that happens in the fabric, right? And I talked about some of the things we're doing in the fabric to reduce the amount of communications time in the fabric by eliminating tail latency and increasing bandwidth. But on the other part of this, what you want to do is you want to offload the compute from having to do any communications and do as much overlap as you can between the compute and the communications. And that's where the feature highlights for the HP Slingshot NIC come into play, because we offload a significant amount of communications to the NIC. Let me give you some examples. We have a really good implementation of tag matching with strong progression, and that keeps your processing and communications moving asynchronously without burning host worker threads or memory bandwidth. So again, one way you improve this. Another way is we have ways of pipelining communications into the NIC. So you can send more data without having the NIC go back and access host memory, as is typical. And when you're doing these small the small packet transfers, that overhead becomes as much as the overall communications as a whole. By doing this pipelining, it becomes extremely efficient. We have ways of triggering operations on the NIC without having to go back through the host. This is particularly useful for complex operations using GPUs, where you want to be able to trigger asynchronous communications without having the GPU go back to the CPU just for the communications part of the stack. And likewise, when for reliable delivery, we have ways of assuring that the packet has been received without having to go back up through the host stack. So those are some of the examples of offloads. Now, there's some other ones that I find are really exciting because they really illustrate how the combination of this NIC and the fabric can take advantage of each other. And an example of that is how we offload rendezvous message passing. So with a rendezvous message passing, the destination node is requesting the packets from the sender. And with Slingshot, with the Cassini NIC, it will assure that the ordering is correct on the receive side in the NIC hardware without going back to the host. Taking it to the next step, right? It'll initialize and finalize the transfers using an ordered flow. Okay, so again, we talked about we could do adaptive routing with ordered flows, but with unordered flows, we could do it on a packet by packet basis. And so here we'll do both, right? So we'll initiate it with that ordered flow, but we'll allow the bulk data component of the transfer to be adaptively routed using an unordered flow. So that's another way that these fabric capabilities, like our fine-grained adaptive routing, not only help with efficiency of the system by letting you consume all of the bandwidth that you have, but also improve your application performance when used intelligently in conjunction with our NIC. Now, all of these capabilities in our NIC are exposed through standard libfabric software interfaces. And that means that the open source MPI community and other platform developers can utilize it. And we've done this with our Cray MPI, so it takes full advantage of these Slingshot capabilities. Again, part of that being a solution, and that includes making sure that these GPUs can do this asynchronous communication, for example. And since Cray MPI has application binary compatibility with other open MPitch libraries, users can get the advantage of these capabilities today, even for codes that weren't originally written with the Cray programming environment. So in summary, on the HP Slingshot NIC, it's really all about delivering supercomputing class performance and fully delivering or fully utilizing the capabilities of the HPE Slingshot fabric. So I think I'd like to wrap up here and talk a little bit about our future directions. Not ready to go into a lot of detail today. Maybe at the next year's forecast, we'll be going into a lot more detail about our future products. I will say that in 2022, we're very focused on delivering these exascale systems, and we have quarterly releases of our Slingshot software that are adding capabilities. Some of the capabilities that are widely anticipated is we have collectives, right? There's other capabilities in our system that I didn't talk about. One of them is collectives. We will add collectives capabilities with our switches through software enhancements coming out later this year. Another eagerly awaited capabilities is things to help isolate traffic, right? We do that today with VLANs for Ethernet traffic, and for traffic that's using the Slingshot native RDMA protocol, we'll have a capability called VNI that will let you have similar capability to isolate traffic, but even more granular than VLAN. So you could use it to isolate tenants, and more importantly, use it to isolate jobs from each other. And there's quite a lot more capabilities as well planned for the roadmap for 2022. But the main message of this slide is that we are investing for multiple generations. You may have seen the article that published in the Next Platform last week or the week before, really talking about our collaboration with Ayar Labs to add silicon photonics to future Slingshot interconnects. And again, the message is we're investing in multiple generations. Work is well underway on multiple generations. In terms of how we're thinking about these future generations, a lot of it is the same value vectors we have today. In particular, this value vector of efficient performance is really, really important. Moving to the next speed of interconnect, which is going to be 100 gigabit per second SerDes, it's expensive. And having twice the performance at twice the cost is not really efficient performance. We get very good bandwidth scalability today with our existing interconnect. For example, those GPU exascale systems, they all have 800 gigs coming into each node. And we scale those very efficiently, in particular with that bladed architecture where you just slide in a couple more switches if you want more bandwidth. Another thing we're very much focused is on heterogeneous processing, right? The industry is not eager to see captive interconnects lock you into a particular processing vendor. And so that remains a focus for us. And of course, scale and performance. Now, we will be adding performance with the next generation of speeds when it's efficient for those growing data set sizes. We are working on ways of adding more flexibility to our system. The fact that it's Ethernet opens up all sorts of possibilities for what people want to do, and we're somewhat constrained in some areas of what we'd like to do. And so in the next generation, for example, enhancing our capabilities in virtualization and supporting slower speed connections and connecting up to more standard Ethernet devices with expanded interoperability. So I think let me pause here, and if there's any questions, got a couple of minutes left. Otherwise, please feel free to drop me an email. Let me flash up my email address here if you want to follow up. And happy to answer any questions one-on-one in addition to with the time we have remaining.
Thank you, Jesse. Very, very comprehensive. Any questions for Jesse? No, they understood everything. Thank you, Jesse. Look, very comprehensive, very exciting. Thanks a lot. Jesse is delivering this presentation from US, so I may ask him to sort of continue and go and have a sleep or a beer before that, whatever you like. Thank you.
Thanks.
Okay.
Thanks,
Our next speaker is from NSCC. It's good to have now a physical speaker again. So Hiew is the senior HPC analyst working with NSCC. He has a Bachelor of Engineering from NTU, and I've known him now for the last few years. He has a very exciting topic today of sharing his learnings of using Red Hat on a Cray system. Cray typically had its own operating system, which is loosely based on SUSE Linux. So it's interesting what these guys have been able to find out. Over to you. Thank you.
Hi, everyone. I'm Hiew from NSCC, and I'm working in NSCC as a senior HPC analyst. Thanks for the opportunity to share our experience in using the Red Hat-based Cray EX systems. Typical Cray systems, they are running on Cray OS, and we will be one of the first users using the Red Hat-based Cray EX systems. In NSCC, I work a lot on software optimizations and benchmarking. In Aspire 2A system, I will be helping in the software builds to make sure the applications run at best performance. Before NSCC, I was working as a software developer, spanned across multiple domains over the years, particularly on software optimizations for GPUs, multi-core CPUs. I have done MPI parallelization optimizations for CFD applications. So for those interested in parallel algorithms, cache optimizations, scheduling, feel free to contact me for further sharing and discussions. As the Aspire 2A is still under construction, so we are fortunate that HPE provide us the bridging system so that we can experience the Cray programming environment as well as the Slingshot interconnect before the Aspire 2A system comes live. So these are the hardware and typical software you will find in a system that you have the scheduler and compilers. So what do you get from a Cray programming environment? You will have the core HPC libraries installed, and also the programming environment for different compilers. What are the advantages of using the Cray programming environment is that they maintain multiple versions of compatible libraries. So as you build your library now, the next month you might have new versions of libraries available. So you have the options to use the latest versions, or you can stick to the older versions so that your existing applications can keep running without disruptions. What is different in the environment is that how we compile the MPI program. In Cray environment, we compile the MPI applications with the cc main.cpp, for example. We don't use the typical MPI-CC in the standard Linux cluster. The advantage is that the compiler wrappers helps you to link to the correct libraries that is compatible to the compiler that you are using. It is very easy to switch to a different compiler. For example, you can switch from Cray compiler to Intel compiler easily. From our user, the feedback is that it is always good to have options for multiple compilers, because one compiler may have problems with running your applications. Then you can easily switch to a different compiler without spending too much time on debugging and troubleshooting the actual problems. Hopefully that different compilers and different versions can help you get rid of the execution issues. In Cray XC system, I find that it is very easy to use the huge pages feature that helps to reduce the memory access on large data sets. In a typical Linux system, you will need to root access to run a command to enable this. But in a Cray system, you can just use a module load to load the huge pages, so that when you build and run the application, it will leverage the huge pages feature that you can take advantage when you are running on large data sets. NSCC as a national platform, we value the open and portable system a lot. So we like to have systems that support multiple platforms and software environments. Very important is to be inclusive of the applications. We are not just running MPI applications, but we also like to run non-MPI applications, for example, the AI workload. So in contrast to the Cray extreme scalability mode, on the right-hand side of the slide, it shows a common setup of Cray system with the extreme scalability mode, that you submit a job through the login node. Then when you run the serial execution, it actually runs on the intermediate mom nodes. That might be a surprise to new users to Cray systems. And through the mom node, it will dispatch the MPI applications to the compute nodes. So one problem with the mom node is that as you have many jobs running, it might blow up the mom nodes. Typically, the mom nodes might not be having huge enough memory to sustain too many jobs. And when we perform resource requests in the jobs through the job scheduler, we are not specifying the resource required in the mom node. In a typical Linux system, instead we submit the job through the login node and run the serial execution and parallel MPI program directly on the compute node. In this setup, you might not have the base. You might not incur some overhead in the latency, because your MPI run is running in the compute node. But on the other hand, you can run any large serial execution and parallel execution on the nodes without problems. The Cray EX system SPI2A that we have is more like a typical Linux system. In addition, we have the slingshot interconnect that we can run many non-MPI workload. Compared to the Cray XC, the ESM mode, there's no direct access from to the compute node using SSH. So we value the inclusive for non-MPI applications. Having access to the compute nodes sometimes gives you the advantage of diagnostics. when you run a job, you have a chance to check whether your jobs is running correctly, whether your MPI configurations are correct. Without this access, you might actually run with the wrong configuration, and only at the end of the execution, you find out you actually wasted a lot of CPU time on that. We usually argue that to achieve the best performance, you need to run with the X software, preferably from the same company, the X hardware. But I would like to argue that why don't we ask about how bad can it be if I run software Y? If we can run with alternatives, we have the options to push for more portable HPC software builds. So the challenge I comes up with is whether we can run applications without the Cray programming environment, so that I have the option to go for more portable HPC software builds. So I take this challenge through the MPI programs. We built several MPI implementations that is available in the industry, the Argonne National Lab MPIC, the Cray, the Open MPI. Then for the Cray MPI, we have two versions. One is using the Cray programming environment. The other one is we use manually linking to the libraries of the Cray MPI. So from the OSU MPI bandwidth test, we find that even though the slingshot interconnect is compatible with Ethernet, that we can use Open MPI and a standard MPIC, but it doesn't perform as well. Compared to the Cray MPIC, it performs much better in the performance, that we can achieve 12 gigabytes per second. Similarly to the latency, if we are using the Cray MPIC, we are getting a lot lower latency in terms of 2 to 3 microseconds. Compared to the Open MPI, you are incurring like 15 or more microseconds of latencies. Interesting part is that whether we are using the Cray environment, we are achieving the native performance. So by right, we can just link to the library manually if we wish to achieve the same performance. So we achieved the first challenge. The next challenge is that, can I build on Argonne National Lab standard MPIC libraries and run on a Cray MPIC? So the MPIC ABI is one of the initiatives to ensure the compatibility among multiple implementations derived from the MPIC. So what is defined in the ABI is, at high level, they are compiled to a standardized naming convention, so that it will look up the right library like libmpi.so, and the .12 is referring to the versions. So as long as you are running the same version of the MPIC ABI compatibility, by right you can run run the applications built from multiple implementations. So does Cray MPIC supports the MPIC ABI? So we try to compile using the Cray MPIC and linking by, this is not using the Cray programming environment. We just link to the Cray libraries directly. And we find that it is able to link to the ABI library provided by the Cray MPIC, and we can run it successfully. Looking at the performance, we can also achieve a good performance similar to the number you are running with Cray programming environment, Cray MPIC. So that is a good thing, that Cray MPIC supports the MPIC ABI. So the third challenge I have is that, can we do the reverse, build the applications using the Cray MPIC and run on the Argonne National Lab MPIC? So below shows that we are compiling the MPI programs in Cray programming environment. And using the LDD command, we can find that it actually references to libmpi gnu.so library. So if we run this program on a standard MPIC program, it will not able to find the MPI library because the naming convention is different. I can understand why Cray MPI choose this approach. Once you compile the MPI program, it links to the correct compiler that you use. So they choose this for that reason. but that sacrifices the compatibility that when you build on the crate MPH, you can't run on a standard MPH implementations. But that doesn't stop us from moving forward. Can we actually build in the container using the standard MPH and run on the crate MPH to get the performance we expect? So I have a container script here. Sorry, this is not. I have the building the MPI program in container. The container runs on CentOS Stream version 8. So we load the standard MPH version and compile it. So and the LDD command shows that it is linking to the standard libmpi.so file. So now here we have the execution script for the container. In this script, it shows that we are bringing in the crate programming environment, the crate MPH into the container so that we have access to the crate MPH, and the munch, the PALS, SD, the PALS, those are the MPI services required to run the MPI program using the crate MPH. The second part of the script, we run multiple versions of the MPI. We test whether it is run on multiple nodes, whether it is able to run the C and C++ programs, and whether it is able to run the bandwidth test properly. So here's the result we get. So we can find that it runs on multiple nodes so that we ensure that the program is actually running on cross node, because running on single node and across multiple nodes might be different. But we see a small little problem. It is not able to run the C++ version. It incurs the simple lookup error that it could not find the libmpicxx.so file. But otherwise, everything else runs properly. So we are able to run the container on the crate MPH successfully. On the C++ problem, I will come back later on that. So on the crate MPH, we have the crate HPE Slingshot interconnect. We found that it is needed for optimized performance. If you are using the standard MPH or OpenMPI, currently you will not get the full performance, but still it might be good for interim solutions so that you can still run your existing applications and provide you some time to port your application over the crate MPH, rather than not able to run at all. So I think being compatible is still a good feature of the Slingshot interconnect. As we experience with the MPI programs on the systems, we find that what is different from the standard Linux cluster is that the crate MPH, they have the default CPU binding. So when you run the MPI programs, it will bind your MPI processors onto different CPU cores. When you are using a standard Linux cluster, they might not have a default binding. So one problem we encounter in this area is that when we try to run multiple threads is actually bind to the same CPU core that we spend some time to find out why it is not actually utilizing all the cores available in the system. But once we figure out how to do the thread mapping properly, then we are able to get it running and utilize all the CPU cores in the system. So with the access to the compute nodes, that helps in the diagnostics. We are able to find the problems much easier. Experience with the crate MPH, so as we shown previously, we are able to run applications built with the compatibility with MPH ABI, but if we compile with the crate MPH, we are not able to run on other MPI implementations. So this is the C++ problem we saw just now that have the lookup failure. So the thing is that the create MPH, it doesn't provide the lib MPI CXX. The C++ binding, the MPI C++ binding is removed in MPI 3. So I do not blame them for not including the MPI CXX in the create MPH. We are so used to the MPI CC way of compiling applications. So even though we are not using the MPI C++ binding, but we are still using the MPI CXX. But instead, the correct way to compile, as shown in the second line in the command lines, the MPI CC-CC equal G++, that is a better way to compile the program we have. We use the G++ as a C++ compiler, but we stick to MPI C binding using the MPI CC. So below the LDD command, you can see that the G++ version, it look up the C binding version of the MPI library so that it can run on the create MPH without problems. The issues we have with the MPI compilers, as create is using a different ways of compiler MPI programs, but we are so used to MPI CC way, and there are so many existing build scripts in the internet. Many build scripts might fail to find the appropriate MPI compilers in the create environment. But fortunately, this is rectified over the years as people try to support create systems specifically. They would detect whether you are using the create wrappers and do differently so that it can detect the MPI compilers properly and compile. The next problem we have is that when we are trying to build a MPI program, we face the problem with the internal compiler error. That even though you are just using -02, it incurred the error. But fortunately, we are able to work around this with -00 or -03. So this might be a moment you might want to try with different compilers or versions to find out whether you have the same problems. So you have the options to use different versions. So if you have only single version, when you get into this problem, you might have to fix this problem in order to continue. And the fix might not comes in time for your applications to run. The fix might be available in the next version, and the next version might be next month. There's nothing perfect in the compilers. The create compilers might have problem at one time, but Intel compilers or AMD compilers might also have their own problems. We have users' feedback is that when they use Intel compilers on certain optimization options, they might have a problem of running into the not a number problem. That as they are running a very large data set, it could incur the floating point errors. So in that case, they switch back to create compiler and run it. On the programming environment, we also find that the Tmod version is not compatible with what is provided in the Red Hat 8. Tmod is a software module that we use to manage multiple versions of software libraries and applications. So it might fail to run certain module scripts. So we might need to find a way to make sure they are compatible. So we hope this might be rectified as the CPE updated to use a new version of Tmod. In the create programming environment, we find that it uses automated module script generations a lot. In my opinion, that might also hinder the user extension, that it is more difficult to extend the modules in the create PE due to many automatically generated scripts. there are many more components to explore in the Cray systems. For example, the CUDA environment, the ROCm GPUs. The Cray also provide optimized scientific library, the libc. So we hope there will be time for us to explore, as we are looking forward for the new system to try out all these components. So my conclusion, the HPE Slingshot, it provides the compatibility, but at the moment you still need to use the Cray and pitch for optimum performance. We managed to run Singularity container on the MPI applications and achieve the native performance. So Cray, in my opinion, the Cray EX is a more open system compared to the Cray EX. I would like to also take this opportunity to thank HPE for providing the bridging system so that we have the chance to test out all the environments before our Aspire 2A system becomes available. Thank you.
Thank you. Very good presentation. Thank you. Any questions for Shinye? No? Okay. Well, I guess everyone is hungry. So it's a lunchtime. What we're going to do is that we're going to go back to the main hall where we were served lunch yesterday. So it's going to be 12:30 to 1:30 lunch, and then we come back sharp at 1:30 for another NSCC presentation by Paul Hiew, who's going to talk about the new supercomputer and give us an update. And of course, there are remaining two sessions in the day, including the panel session. Those who are joining us virtually, please do take lunch, or if you're in the evening, whatever, dinner, coffee. Okay, we are going to start our post-lunch session very soon. So if you're hearing this, because if you're tuned into this channel, please do come and make to the room. We're going to have an exciting presentation from Paul Hiew. I was going to talk about the Aspire to a supercomputer. I'll probably give another minute for people to come back from their lunch. It's probably making a way, so just another minute. Meanwhile, you can read Paul's bio up on the screen. I know Paul for many, many years, and Paul has also worked in SGI before and has been in NSCC for a very long time. Obviously, as you can see, he's graduated from UK, did a Bachelor of Engineering there, and has been in HPC for about 20 years, just about like me. So 20 years. So Paul, I think what I'll do is that I'll invite you, please come in, because I think people can come and join. Welcome, Paul.
Hello, good afternoon. Hope you have a good lunch. And those are on offline, might be you are on the late lunch or whatever. Yeah. I will start with something which is less that heavy. It's more about today's all the presentation in the mornings, the presenters, all the things that we start to put together on our system that is we just recently is still on the stage of assemble and implementation and installations. Okay. So some background on NSCC. NSCC has its first petaflop system in March 2016 that is being commissioned, and it's almost like 6 years by now. So yeah, we are in the midst of going on into the this new system, and of course we are looking for future system at the same time. For the current system that we have, the main system is actually a 1 petaflop system. It's around 30,000 core, and it's spread across 21 racks. This is very important because I will share with you with the new system. So the next one is we have a high-speed interconnect through the SINGARAN, the Singapore Advanced Research and Educational Network, that link a few important locations together, especially paying attention to these 3 yellow box, NTU, NUS, and A-STAR. This is where one of the some resources will be allocated, locations. This is the specification of the summary of the specification of the hardware on the new system that we recently purchased. Okay, the new system is 800 nodes, but it will be contributing around to totally 105,000 core, which is 3 times. That's why it will be across just now the one that I mentioned about 30K. So we will be consisting of 2 types of CPU. One is the normal CPU, the 7713, and then another type of CPU we'll be using is the 75F3. And the total storage of the thing is around 476 terabytes of memory. And then we have 352 of this GPU cards. That is the A100. So some facts about it. By number of cores, we are 3.54 times compared to the current system. And it's less nodes. So it's 1.5 times less than the current number of nodes. But it's 5 times more compact because right now we have less number of racks. Remember just now I said 21 racks. Now it's reduced to some numbers. Let's see. Whereas the GPU, we are only 2 times of the current GPU, the sizings. Let's look at the new data center that we're having. So the data center is located at the NUS I4, the Innovation 4 building. And the data center basically is divided in Area A and Area B. What's the difference between Area A and Area B? Let's look at Area B. Area B basically is a kind of normal data center, which the environment have some cooling. But whereas Area A, the environment is totally no cooling at all. So whatever cooling will be within the racks, so the computational. So when it's ready, you are welcome to visit and you'll get the feel of sauna. So this is just a brief looking through. So the main host of the thing is the top one. There's 768 nodes, the red color that is on the tray. So this diagram is divided into Area A and Area B. Okay, on the left-hand side will be the Area A. On the right, I think the direction is a bit different from mine and yours. Okay, basically it's Area A and Area B. So we try to match it. The CPU that is the main for workhorse that is the red color, and then the GPU will be in both locations will be a slightly different design. One on the area A will be the 4 GPU, whereas the area B we have a 4 and 8 GPUs per node type. Whereas we have some large memory nodes on the area A. We also have some large memory nodes on the area B, and we have a high frequency nodes over in area B. So this is a detailed hardware spec. So I will group it. This one is main system, large memory, and accelerated nodes. So this is how the category goes, and then I box it with the area A, which is under area A, and which one is under area B. This is the high frequency node, so you can see that because of the clock speed is higher than it, but it's hotter. Okay, so basically, yeah, this is for a specialized kind of workload that we are looking at. And where else come to the storage, we have basically two types of storage that we on this new system. Basically, we have the Luster, which is for the scratch, and then we have the GPFS incorporate with the DMF for the persistent storage. So I will talk about slightly more about the DMF slightly later. Okay, let's go into looking at the Cray EX itself. This is the layout of the Cray EX that we on our system. Basically, you have 4 cabinets. Okay, 4 cabinets compared to the 21 racks that we have. So all the number of core is 3.53 times, but it's reduced the sizing all the way from 21 racks into these 4 cabinets, and it's yet more cores. Let's look at the, I think this morning the presenter already shared with some of the diagram, but for us, we have slightly one more CDU at the side. So it's both sides have the CDU and then the 4 cabinets in between. Okay. So this is the delivery on the first cabinet. Okay, those are the people on the ground. I think we didn't take the photos of some of familiar face. This is the shipping in of the racks. So yeah, it's quite heavy. So this one is front end and rear wheel for this one. This is a rear wheel for the thing. Okay, but for the photograph you won't see the difference. So this morning also, presenter also did share about the slingshots. So there are 2 types of slingshots. Okay, switches that onto our system. Remember we talked about the area A and area B. So the area B will be the one using the air cool kind of switches, whereas the area A will be using the liquid cool system. The switches. But both of them are the HPE slingshots switches. So this is some of the work in progress of the software stack. This morning, the presenter also shared about the software stack that we'll be using. For this system, we are not using the conventional Cray OS, so it's more generic and more open system for familiar with our NSCC users. So yeah, it's something new, and once the system is able to access, do give us a feedback about it. Let's look into the interconnect itself. So we remember we have 4 cabinets. This is the main big circle. There are 4 main big circles over there. So those are, each of the big circles is representing 1 cabinet. So there are 4, and then because of area A and area B, we have a massive bundles of this slingshot will be around 2.4 terabytes per second transmission over both directions, area A to area B. So look into it. What is this big bubble look like? What is actually, this is called the group. So inside there, so each of the group have 16 small little circles, and each of the small little circles are connected to 16 nodes. So 16 times 16, this is around 256 nodes per group or per cabinet, you like to. So this is good for people who are doing programming, so that you optimize your coding and placing your process into a more appropriate. So each of the small little circle is actually 16 nodes. Will link with the 1 slingshot switch. So from 1 slingshot switch will be linked a multiple bandwidth. This is around, you will see, is around 400 BPS. So the wording will be a bit small. You can't see it. So this is another part I want to share is about the area A. So the area A, we will be consisting of most of the components will be the storage, where the login node, the visualization nodes, and all the administrative nodes. So all of them are linked with the slingshot to as the computational and data transfer network using the slingshots. So where else we are migrating the servicing administrative nodes using the HCI hyperconverged infrastructures. So we are moving away from each of the nodes are dedicated as a physical for administrative. I think in the HPC world, we tend to do that. You know, one single node will be doing an NTP, one single node, physical node will be doing, like, for example, the scheduler, you know, or gateway. But we are migrating away from that. We are using the virtual machines to do that, so that it gives us the flexibility and resilience when there is equipment failure. So now we have to touch about the DMF. It's called the Data Management Framework. So basically, I did do a presentation about the DMF. Basically, as a storage, it will be using a tier. So from here, we have Lustre, we have GPFS. So these are two types. Of course, it will have the XFS, you know, the rest. We'll be using this framework to move the object from the file system away so that we can free up the storage itself. Why is critical? I will show it to you later. There is some statistic report from our system. So just bear in mind, you can just move your data, the object data, away from the main storage, the spinning high-speed storage, but yet it is not lost from the user perspective. That is the most crucial part. If you ask the user, is your data important? They always come back to tell you, yes, their data is always important. They want to access now. Okay, but yet, is that true? Okay, let's see. So this is the idea about the data DMF itself. Basically, you on the other side will be the spinning disk, the high speed. Maybe you having the SSD, you know. Where else we have the nearline. So this is, for example, we have the 0 watts storage, and then the other side we will be most of it can go to cloud, the S3, or to using the tab to do the coldest data of all, because some of them tend to forget to access the data. They just want to dump it in the storage itself. So this is the current setup. We have the infrastructure at the NSCC. That is in A-Star, the Fusional Polis, whereas we have the data to be moved across our high-speed network all the way to NTU as a DR, disaster recovery sites. So in NSCC, our data actually have a copy at the remote site. So anything happen in, okay, touch wood, everything happen on the Fusional Polis, your data is safe. So this is the summer practice. But for moving forward, when the new NSCC facility is up, we would like to do the same thing for the new site. So we're still taking the NTU as the remote site, disaster DR recovery sites. With this diagram, this is directly mirroring the whole design without any consideration. But after we study carefully, this is what we're going to do. So we will be incorporate a 0 watts, will be act as a staging that is actually also freeing up the colder data, not that frequently used data, to be offload from the main high-speed storage. So before, and then also make a copy into the NTU site, so that act as a DR recovery. So, but yet you see the data basically will be flying around the whole west coast of Singapore. from Central all the way to the West Coast. So basically, the logical point of view, the storage is go like this. From the NSCC, the storage will be going to the 0 watts before it going to the NTU. You can see that there are two round cursor there. So whereas the NSCC facility, the current one, we will redirect the traffics all the way to NUS before going back to NTU. So this is roughly some of the equipment's drawing. So this is how the flow of the current and the new system. So this is very important here. You can see that this is the two file system that we have. One of the file system is mix of general users. The bottom one will be mainly for the genomic based users. You can see that most of the data are actually pretty old. Do you notice that? You can see that actually average is only around 14.9% of the storage actually you require to be considered recent. Okay, so over here you can see that actually for the general usage, we only require to provide 25% of the spinning high speed. Then you can basically cater all the way to house the 1-year-old data. Whereas for the genomic base, it requires even lesser. So that is the nature of the user. So this thing we study based on the modified DAT and the SSDAT. For those who are familiar with Linux, so you will know that this is how you're going to know you usually try to evaluate whether your data is considered cold or hot data. Okay. So basically, this is some of the design detail that will be incorporated onto the system. So these are this is some of the software stack and then things that we'll be putting onto the system. Okay. Yep, that's all for me. Yeah. Any questions?
For Paul? No? Okay. Well, thank you so much, Paul.
Okay,
Thanks a
thank
lot.
you.
It was a fantastic presentation. Thank you. So next, I believe we have a virtual presentation. It's going to come from Steve Tolnai. Steve is online? Yeah. Okay. And Steve is going to talk about the next generation of cooling or how to cool these next generation of HPC and AI servers. Steve has been as a face of HPC in APAC for as long as I can remember. More than 30 years. He's been 35 years in digital, compact, HP, and HPE. And internally we call him like the godfather of HPC in Asia. So with that, I would like to welcome Steve. And Steve is up. I can see him. And Steve, off you go.
Thank you very much, Raj. Okay, we just get some slides up here. Oh, there we go. Excellent. So good afternoon all. Steve Tolnai, as Raj mentioned. It's a great pleasure to join you for the first HP cast moving to ForCAST in Singapore. Renaming of the conference from our perspective, trying to make it more open and not so much linked to the past with the HP, but as we move forward with HPE. Today I'm going to cover the challenges and how we can meet those with cooling solutions for HPC and AI servers. Okay. Bit of delay there in the slide movement. Continually raising demands in the world of data and computing is evolving. We see powerful new systems often outpace existing cooling infrastructure, and these can limit the effectiveness of overall IT. We're quickly moving to the age of insight. This is all being driven by the need and the ability to collect and synthesize massive amounts of data using ever larger models, new algorithms, and a massive growth in data. The result of this activity is a crisis coming in cooling of CPUs and GPUs. Over the last few years, we've seen CPU power draws rise, with 350 watt CPUs being released this year and 550 watt CPUs expected in the next generation. The cooling dilemma for us all and for HPC and AI servers is becoming a greater issue to resolve. In parallel, GPUs are following the same rapid increase trend, projecting to reach 700 watts to 1,000 watts in the near future. If you go and ask the GPU vendors, they'll share their lovely roadmaps of what's going through the roof effectively. Today, as an example, AMD with the latest generation of MI250X is at 560 watts per GPU. Compounding the problem, silicon has gone to 3D. Parts are now being layered on top of each other, which creates a thermal challenge as we can only effectively cool the top of the chips. As these two trends begin crossing, cooling high-end parts gets really challenging for not only us, but the whole marketplace. Though it's possible to cool some high-end parts with air cooling, it results in the use of enormous heat sinks, increasing the server size overall, reducing density and driving up the costs. Next generation GPUs for air-cooled alone are trending to 5 or 6 rack units. That's 22 to 26 centimeters, for those in the metric, for that, and that's just for the heat sinks alone. So we're going to see some really increasing in larger systems because of the thermals to cool the GPUs. So customers are looking for a holistic cooling solutions from us that closely match their performance, energy efficiency, and sustainability initiatives. So that's where HPE is coming in here to help with data centers as IT management consider more options and constraints than ever before. So in the past, performance has been one of the most important benefits of liquid cooling. It provides effective cooling even for the most powerful chips while they operate at the highest possible performance frequencies. As the industry tackles the needs for greater energy efficiency and both lower CapEx and OpEx, liquid cooling also shines for those respects. Here's an example to illustrate the cost savings of using a liquid-cooled HPE system over a 5-year period. When comparing the power usage of 6 full racks of air-cooled servers versus 6 racks of liquid-cooled servers, the cost savings are significant in the 86% order of difference. These savings alone from the first 5 years can be reinvested to increase the cluster size from 7 to 10%, or in this case here, 37 additional servers could be added. With the acquisition of SGI in 2016 and Cray in 2019, the combined technologies of these groups under one organisation has ensured HPE is able to provide future-proof solutions that closely matches our customers' needs. From a technology perspective, HPE today has 487 granted thermal patents, 256 granted power patents, 468 granted mechanical patents, and over 250 patents pending. The DCTS, or Data Center Technologies Services from HPE, and the Point Next teams also provide guidance to those looking for in-depth review of their facilities and liquid cooling infrastructure and planning. Installation and ongoing service support are important activities managed by these groups, and they ensure that our customers have the peace of mind to keep their data centers running smoothly. And these guys, this team, they operate around the world, and we bought a company called, I think it was called EP several years ago, and many of them are still part of our DCST team. Our HPC and AI customer requirements are consistently evolving based on shifting priorities and the progression of their own goals. We can see from across this, there are many types of different data center requirements. Understanding the various phases makes it easier to provide product recommendations in an overall solution. 3 key phases help us segment the HPC and AI server choices, together with the rack choices for different data centers. At a high level comment, these racks and the kilowatt ranges align to the solutions that are most appropriate from a cost, efficiency, and flexibility standpoint. There are always outliers to when mixing and matching solutions, but in general, these are good guidelines to start with, especially when picking a solution for your data center. Let's have a look at the first phase, the 10 to 20 kilowatt for liquid cooling solutions. HPE has the most comprehensive liquid cooling portfolio covering all types of HPC and AI servers and needs. The portfolio can be divided into 2 parts: cooling solutions that use liquid to cool the air that cools the IT, and second, cooling solutions that bring liquid directly to the server components such as memory and CPU. RDHX, or rear door heat exchangers, and ARCs, adaptive rack cooling solution, use facility water to cool air directly around the servers. They are more energy intense than hybrid and direct liquid cooling options that we'll cover later, but offer in many cases more flexibility. To have a little look at a rear door heat exchanger, or the RDHX. Rear door heat exchangers are used for cabinet level liquid cooling. Hot air exhaust in the cabinet rear goes through the cooling coils. Heat is moved from air to water. Typically configured as a room neutral cooling solution using direct facility water feed, or with a CDU, coolant distribution unit, is the most prominent of these types of installations. Another alternative, the HPE ARCs adaptive rack cooling solution, uses a closed loop room agnostic design capable of cooling fully populated racks, even with top bin CPUs and GPUs. The horizontal airflow of the HPE ARCs fully supports all industry servers and storage with front to back hardware cooling. So what this means is not only can HPE hardware be installed, but also other vendors' equipment as well. It's a very agnostic solution. And you can see the cooling the cold air is driven out the front across the server racks on either side, and then the CDU in the middle and the large air fans draw it in and exchange the air to liquid cooling. The acoustic benefits of this solution reduce the number of water taps, also bringing advantages to the overall rack level cooling products. So we only need one set of water coming into the middle section of the rack there as an example. The HPE ARCs has solid front and rear doors, and associated IT racks also have those with it. This helps lower frequencies and overall lowers acoustics compared to smaller fans that are exposed to the data center in other types of solutions. Acoustic foam on the front and rear doors of both the ARCs and the IT racks reduces acoustic emissions, meaning that it's a much cooler, a much less noise environment in the data center, which if you've ever been into a data center with a lot of HPE systems running at full speed, can be very noisy. RDHX, rear-door heat exchangers, are often compared to ARCs. Here's some comparative details. Both provide rack-level room neutral cooling. Inlet water temperature can range wider with the ARCs. ARCs acoustics is lower than typical rear-door heat exchangers, through to using a different footprint for the ARCs. ARCs requires no data center airflow management, it's totally enclosed, and whereas the rear-door heat exchanger pushes heat still back into the room or pushes air back in the room that has to be managed. But then again, the rear-door heat exchangers is seen as a more industry standard technology. ARCs offers a unique advantage to HPE customers. It was originally developed for large deployments of HPC in the defense industry. So it's very well proven across defense and now other customers as well. From a high level, each solution provides different benefits, costs and constraints. In general, rear-door heat exchangers and adaptive rack cooling system have a lower upfront cost than other HPE liquid-cooled solutions, but are typically more expensive to operate over time. Similarly, RDHX and ARCs generally require cooler or colder facility water than other solutions, making them more suitable for lower density racks. Turning to phase two, the 20 to 50 kilowatt style racks, very much becoming the norm for our HPC customers across the world. There are typically these are typically for customers investing in the future to keep up with GPU and CPU technologies. They prefer to limit the limit and have flexibility on the infrastructure, such as using standard racks and air cooling, coupled with liquid cooling for powerful systems. Let's have a look at some of the typical phase two style customers for liquid cooling. As I previously covered, the liquid to air cooling, rear-door heat exchangers and ARC solutions use facility water to cool the air directly around the servers. On their own, they can provide air cooling for racks up to 60 kilowatts. They're more energy intensive than hybrid and direct liquid cooling options, but offer more flexibility. Hybrid cooling with Apollo DLC manages server IT by directing coolant through cold plates. These sit directly on the hottest IT components inside the server. Coolant flows through these cold plates to capture the heat and is pumped away to be cooled elsewhere, typically outside the data center. It is very energy efficient and effectively cools the most powerful CPUs and GPUs on the market without the common thermal issues resulting from air cooling. In cases where higher rack capture or room neutrality is required, Apollo DLC can also be combined with RDHX or ARCs to capture the IT heat. Oops. The Apollo DLC provides DLC direct liquid cooling to the hottest components in the server, such as the CPU or GPU, while using air cooling to cool the remaining of the heat components. You can see up the top right-hand corner there, there's two little orange nodules, if you like, or taps. They're the connection. The liquid flows in across the GPUs or processors and then back out of the server again. The racks typically come pre-installed with rack-mounted CDUs and manifolds and can be 100% liquid cooled when accompanied with the RDHX and ARCS capabilities. The facility water can be fed from the top or the bottom, as we can see down with the racks there. The feed-in is showing at the bottom. Just looking at an outline of the components, to the left is a standard 42U or 48U HPE IT rack. Inside the rack shown on the right is the key DLC components that we add in the factory. The DLC manifold, rack mount CDU at the top of the rack, and the Apollo servers throughout the rack. PDUs are vertically mounted on the side of the rack to reduce wastage of rack space for servers, so we can get the highest density in the racks. A comparison from a high level, each solution provides different benefits, costs and constraints. In general, RDHX and ARCS have a lower upfront cost than the Apollo DLC solutions, but it's more expensive to operate over time. Similarly, RDHX and ARCS generally require colder facilities water than the Apollo DLC liquid-cooled solution, making them more suitable for lower density racks. Turning to the third phase of customers with large requirements for HPC AI servers, it's becoming necessary for many of these racks requiring 50 kilowatts or more to be driven by density and the best data center utilization. Typically, customers driven by ambitious agenda, such as NSCC, as we just saw from Paul's presentation, to get the best performance possible, best data center PUE, and overall total cost of ownership. And so the larger data centers like NSCC and Pawsey in Australia and others that we're working with in Asia Pacific tend for the larger rack deployments to look at this third phase. Let's go through and have a look at some of the customers in this third phase of style of liquid cooling. So extending HPE's comprehensive liquid cooling portfolio to cover all types of customer needs, and this especially at the higher end for supercomputings. The hybrid cooling with DLC covers IT server heat by directing coolants through the cold plates that sit directly on the hottest IT components in the server. Coolants flow through these cold plates to capture the heat and is pumped away to be cooled elsewhere. It's very energy efficient and effectively cools the most powerful components on the servers. In cases where higher rack heat capture or room neutrality is required, Apollo DLC can be combined, as I've covered, with that Riedel heat exchangers and ARCs to capture 100% of the additional IT heat. The Cray EX and Cray EX Lite on the right-hand side supports the very highest density servers with 100% liquid cooling. These offer the lowest TCO capabilities and when scaled and offers the best performance, energy efficiency when they're looked as the major requirements. This solution can also resolve critical density issues that cannot be solved by the Apollo DLC. For example, deployments exceeding 1,000 nodes, we typically look at the Cray EX as a better alternative to the Apollo DLC, and then the Cray EX Lite would typically be used for deployments under 1,000 nodes. The Cray EX provides 100% DLC direct liquid cooling to all components in the server. So this includes the latest top-end CPUs and GPU technologies also memory, voltage regulators, etc. in the server. The Cray EX is the best option for high performance computing and AI deployments exceeding 1,000 nodes or servers. The large row-based CDU, you can see at the far left, manage the coolant distribution for the multiple racks. As an example, the Cray EX blade to the top left on the diagram there has 4 nodes or servers in the one blade. It's 100% direct liquid cooled, and the Cray EX offers additionally up to 256 nodes per cabinet. It also comes integrated, as Jesse outlined, with liquid cooled high performance interconnect switches. So the Slingshot are also directly liquid cooled, and supports either top or bottom feeding for water to come in from the facility. Cray EX Lite, this is a new product that we're planning to launch in the second half of 2022, provides direct liquid cooling to all components in the server, similar to the Cray EX, including CPU and GPU, memory voltage regulators, etc. Additionally, the Cray EX Lite will support the top bin processors and CPU technologies. Racks can be populated one chassis at a time and scaled over time. These pre-filled and coolant ready can be connected directly once installed in the data center. Dedicated in-rack CDUs make this possible, allowing additional Cray EX Lite racks to be added to existing clusters easily over time. A little bit a more detailed look. The Cray EX Lite supports up to 96 nodes or servers per rack. It supports either a single or redundant CDU at the bottom of the rack. And as I mentioned, it integrates liquid cooling into not only the servers, but also the high-speed interconnect switches and supported at the top or the bottom facility, similar water feed, similar to the Cray EX capability. So to review on a high-level summary, each of these solutions provides 100% liquid cooling, but through a different combination of benefits, costs, and constraints. In general, Apollo DLC plus rear door heat exchangers or adaptive rack cooling solution is more expensive to operate over time as it includes an air cooling element with fans which need to be repaired and replaced, but provides more flexibility selecting server options because we can use any industry standard server in the ARCs as an example. Similarly, the Apollo DLC plus the rear door heat exchangers or ARCs generally requires colder facility water than the Cray EX and Cray EX Lite due to the need to provide both DLC and air cooling capabilities. One of the important differentiators is the availability of fabric. So often a key choice for customers when looking at HPC solutions. The high-speed fabric with the Apollo DLC enables us to provide either InfiniBand or Slingshot, while the Cray EX and Cray EX Lite is exclusively enabled for Slingshot. HPE is a leading supercomputing provider worldwide with deployments of the fastest and most powerful supercomputing systems. And we're helping our customers to lead research initiatives across multiple industries. By way of an example, Formula One race car design and production, they often have technology that trickles down from the Formula One cars, making its way into consumer vehicles that we see coming out more and more. In a similar way, the advances in technologies developed for supercomputing and the work that we're doing with customers and exascale around the world trickle down into HPE solutions. And over time, this improves the entire HPE offering and our customer alternatives. So in summary, liquid cooling for HPC and AI servers today is a mature technology and is going to be more and more required to provide higher density, energy efficiency, and highly reliable systems in the future. And it's available for multiple industry, and it creates a winning combination for our customers that they've grown to expect. We're designing and implementing future solutions and working closely with our partners, typically the processor, the memory, the GPU partners, to understand the current and future needs and the portfolio of those, which will help us drive the next generation of liquid cooling and innovation offerings to us in our roadmap. Thank you. Thanks very much.
Okay, thank you, Steve. That was very, very good. Any questions? Okay, maybe the trend of the day has been no questions. So
there you go. Why start now?
Well, at least for the next session. Thanks, Steve. Thank you so much for your
oh, wonderful. Thanks, Raj.
Yeah, thank you. For the next session, which I believe or hope is the most exciting session of the day, it's going to be a panel discussion. You have sort of heard that from some of the speakers who are also part of this panel, so I'm not going to introduce everyone, but there are some new panelists, and I think we would like to put a bit of an introduction for the people who are joining now. And also, this bottle, it's a fantastic bottle, is for all of you attendees, but also whoever asks a question will get an extra bottle. So if you have 2 kids, you need 2 bottles. Can we start the? Yeah. Okay. So let me invite our panelists for today. Nick Wilson from NSCC. He's the technical director, acting for just only a little while more now. Very soon, technical director for NSCC. Please come in, please. He's a PhD, so I have a lot of respect for all the PhDs. Dr. Nick Wilson here, from Oxford University especially. And also, he has been in HPC, I guess, for nearly 20 years now, 15 to 20 years. So very, very long time and a veteran, really. After that, I would like to invite Mr. Nelson Dias. He is the Chief Revenue Officer for Altair. Altair is known for many different software solutions. In the world of HPC, it's PBS Professional, as a lot of the people use in Singapore. So that's represent Altair. After that, I'm going to invite Mr. Adesh Gupta. Please come in. He is the Sales Director and Global Account Sales for APAC from Intel. And he has been in Intel since 1999. So a really long tenure there, and has been a very close worker for us together in HPE. And apart from that, obviously, I would like to invite Paul Hiew. I introduced Paul Hiew before, and those who know HPC in Singapore, they all know Paul Hiew. He's from NSCC as well, and a key member of HPC community. And after that, I would like to call Bill Mannel. He's the VP and the General Manager for HPC and AI Group for HPE. Please, Bill, take your seat. Okay, so that's all our panelists for today, and I'll be moderating the session. There are ways for you to ask questions who are sort of offsite online, yeah? They can send their questions in. I have some leading questions that I'm going to start with, and all of you who are participating here live, you can just raise your hand and ask a question, and one of our helpful staff will come in with a mic and let the questions to come through. And yes, there will be an extra bottle for everyone who asks a question. So let me start with the leading question. I will ask the question. You don't have to read to that. But anyway, as we know that HPC and AI is continuing to become more and more common and mainstream. So what is the view in terms of the future of the HPC? And it's continuing that in your experience, when you look at the HPC and AI infrastructure, do you think it's going to largely stay on-prem as it is today, or there is going to be a little bit of shift towards external data centers or public clouds? Anyone who want to start?
I'm certainly willing to start.
Okay, yes, please.
So I think in general, most customers will probably move to more of a multi-cloud type situation, which includes a private cloud for those things which are need more security, very data heavy, these sorts of things, but also gives them some access to other resources, either because they want to test other types of architectures or technologies, or because they want to have a burst capability at certain times of the year from that perspective. So I think that's probably going to be a much more common situation going forward. So it's not all on-prem, it's not all in the cloud either, but a combination thereof.
Bill, Paul, or
Yes, so yeah, I completely agree with that statement. I think there are certain of our users who have a very dependable and high compute requirements, who will expand to fill up any resources that you give them, where I think it makes sense to just have some sort of base load type system on-prem where they can just run it into the ground over many years and just churn out their data results. And there are other users who are going to come in who will have more of a dynamic requirements and more bursty requirements, where going out to a mixing in with public cloud or on private cloud will make sense in that situation. So yeah, I don't think on-prem is going away, but it might migrate up to some of the more higher levels of some of the specialized use, and some of the more general and new users coming in at the bottom will probably be introduced through cloud. And I think, yeah, the difficult thing there is how do you migrate your users up the value chain from, or whichever way you see the value chain going, to make your users be able to use. Yeah, you want your users to be able to choose between on-prem and public, and it not to be a big hassle for them to try and shift their work between them.
Very a thought that I always think is going to happen, but anyway, Paul, any thoughts on this?
Yeah, actually, most of the user, when they have their data is more highly secure, they will be choose on-prem. When the less sensitive data, they will go to public cloud. And users tend to doing experimental, they will be preferred to be on-prem, especially the massive types. Whereas public cloud, it's not affordable to run jobs for experimental base. It's just too costly.
Too costly.
Yeah. Science is about learn from the failure rather than learn from the successful run.
Exactly. Thank you, Paul. Any comments?
Yeah, I just so I'm going to remove.
You can remove the mask.
Echo that comes right through the
Okay.
ears. Well, I'll take the first part of the question, which is the future of HPC, and I think if I were to look back and start, looking at the kind of systems that were getting built back in the 90s and 2000s, you had systems that could occupy as big as this room to give you a teraflop of performance. And I think that was at that point in time to solve the kind of problems that were, whether it was related to climate modeling or life sciences and so on. But I think as we progress through innovation in semiconductors, progress through innovations in the racks and data centers and cooling and so on, in the fabric and so on, you know, the kind of products that were emanating from there to solve the problems became more and more exciting.
Yeah.
And I think as we look at the future over the next few years, the insatiable demand for compute is not going to stop. Customers are going to demand more and more of compute,
Yes.
more and more of network, lower latency, faster access to data, the ability to analyze and solve bigger problems at a pace that was never seen before. And I think it's just the insatiable demand of humans to get things going faster, higher, and quicker.
Yeah.
And I think the future from a high-performance computing perspective is indeed very bright. And speaking from an Intel standpoint, we continue to innovate at the silicon level, innovate at the fabric level, coming out with the technologies to solve different kinds of architectural issues. And I think it's just in partnership with HPE, in partnership with some of the partners we have here on stage. It's to create some unique capabilities for our users to solve the problems that they have.
Yes, no.
So, from our perspective, Altair is both an enabler as well as a user of HPC. You know, a couple of years back, we thought that everything is going to move to the cloud. I think even people like us are moving back a lot on-prem.
Yes.
So I think the hybrid operation will continue for the foreseeable future. It's going to be in between. I think scalability and portability of applications is key.
Yeah.
And you know that will dictate more and more usage. But I think from a cost perspective, it's going to be a hybrid structure for the foreseeable future.
Thank you, Nelson. Yeah, Nelson, yourself and Paul, both of you actually talked about the cost, obviously. And in my experience as well, I've seen that in the end for enterprises or institutions, cost is a big factor. In the end, wherever it makes more sense, that's what's going to happen. Sometimes we thought that, as Nelson said, a while ago, it seemed that it's going to be very cheap to run in cloud. That's why everybody's starting to move into cloud. And now some of the people are coming back as they have experienced. And it's in fact coming back, which has been more painful than even going, because it makes it easier to go in, but it's harder to come back. So, you know, with people, you know, as I said, cost, you know, those things, it seems that they will probably continue to run in hybrid mode. We just also saw that prior to this panel, we had Steve presenting. The CPUs are becoming, you know, taking more and more power. The GPUs are taking more and more power. So there is a bit of a power hunger going on, right, in your data center, which means that an average enterprise or an institution is going to struggle to actually have this specialized data center, because it has to be liquid cooled or some special cooling that is required. While we are happy to sell all of that, but the thing is, at some point, some institutions are going to struggle with that a little. And so I'm just putting on the spot in terms of, you know, with those things in mind, I think, or where I start to see is that it's the likes of NSCC, which is again kind of a cloud for the likes of GIS or NEA or whatever, if you think about it, right? They are the kind of your end user organizations. They all have a little bit of their own data center, but then they're also starting to rely more and more on NSCC for the large complex jobs, because either they can't host it or they just can't, you know, do something like that. What do you think about this kind of trend? You know, this is going to continue, that more and more users are going to, so there may be like this breed of special, you know, HPC centers, and they'll get bigger and more sophisticated while they try to sort of get more and more users. Yeah.
So I think you're correct, but that's always really been the model of academic research computing. It's always been departmental clusters, well, group clusters, departmental clusters, national facilities. So that's always been there. I think the question, an interesting question back is, could the commercial industrial sector sort of copy that in that
Yeah.
universities work together to pool their resources. Could companies pool together rather than a single company having to put in the expertise and the investment to have that data center? Could a group of companies do that together?
Yeah, well, I think I go back to my comment about multi-cloud. So I think the multi-cloud will be, I mean, obviously we have, a number of very large players today that are providing cloud, but at the same time, I think access is going to be broader. I think a federation of different compute capabilities across academia, commercial businesses, as well as the large cloud providers, the public cloud providers, is going to be probably pretty common as we go forward. And to your point, not everyone's going to want to have the kind of data center that is needed to run the most performant jobs. But at the same time, there's opportunity for something a little less than that people can maybe keep on-prem, or there could be possibilities for using that as well. So I think you'll see more of that. And actually, if you come to my talk tomorrow, I'll talk about that.
Yeah. Any other comments on this?
Yeah, I think most corporates like us are, to solve the power and other issues, are moving to co-location sites.
Yes.
Right? So it's kind of on-prem, but co-located to take care of the power and other aspects of it.
So co-location is probably the new trend.
Co-location is becoming huge.
Huge, yeah.
With corporates, but not the model that Nick suggested.
Yeah, I think that's a very good thing, because we starting to talk about, you saw the example of Steve's presentation, that we have a group, a team of data center services group, where we can come in and design and help do data centers, or even work with you, provide expertise in doing all of that. And my feel is that going forward, it may become a point where we may just tag with some data center, as a co-location data center, and then provide the whole thing as a package, and that might.
Well, I think the important thing is multi-tenancy or not, right? So, you can do a colo but still be a private cloud.
Yeah.
Or you could do a multi-tenancy type of arrangement where you're actually kind of sharing resources with other companies and academia and so forth. So
yeah.
I think that's going to be a little bit of the distinguishing factor. So in some cases, you're going to feel comfortable with a multi-tenancy situation. In some other cases, you won't from that standpoint. So you can always go to colo, but then what kind of resources are you using? Are they dedicated to you and maybe managed by someone else, or are they multi-tenant and can be used by a variety of different entities?
I have a question for NSCC again. You guys obviously are the sort of supercomputing company institute in Singapore, and we have seen that obviously Aspire 2A is very impressive, in terms of how compact it is and everything, and with the DC. We can fill in a lot of more cores. But I also saw your plan to move to 10, 20 petaflops. Where do you think is the space in Singapore? And let's say you decide that in few years' time you want to go 20 to 50 petaflops or 100 petaflops. I'm not even talking about exaflop, which is happening in the world right now. But let's say, what do you think is going to be the trend in Singapore?
Yeah, there are certainly restrictions not restrictions, but limitations within Singapore in terms of the climate doesn't help. There's limited power. And there has been a data center moratorium, which has just been lifted, but that's still so that the future is, it's unclear at the moment, but it's certainly a concern for if you're thinking about citing a lot of very large data centers in Singapore, is where is the energy going to come from, and how are you going to cool those down? It's certainly challenging.
Yeah. At any point, if there is any question from the audience, please do raise your hand. Yeah, yeah, Manjunath, can we provide a mic? Is there a mic? iPad. Pass me the iPad. Sorry. Oh, okay. So he has to write the question. Sorry, so he has to write the question so that I can read the question. Then we can tell the question. What the question is. You can probably just say it. I can hear you fine, Manjunath. Just say it.
Give him a microphone.
No, you can't. For some reason they said they cannot give a microphone.
Yes, you are. So yeah, very good question. So let me repeat the question again. So his question is that, like, we have lots of software like HPE. When people are wanting to use hybrid model or cloud, will we be able to make the licensing available to run it on the cloud?
Well, certainly, I'll give you my business card. So, this is one of the things we are looking at going forward. So we do have, as I mentioned in my slide presentation earlier, we have a lot of software that is available, and it does tend to be more cross-platform than others. So you can write code once and then have it compiled and run on various architectures. And so we are looking at whether or not that's a viable option for us to go forward. Would like to get some feedback from yourself in terms of what parts of that are most important to you, how would you use it, what would that look like to use it, those sorts of things as well. So that's something we're actively looking at.
Thanks, Bill. I think Nelson might be good to sort of try to answer some of this, because you are basically a software company, and what about the licensing? Are you making it available on the cloud?
Yeah, so most customers today, for most software, can bring their own license. So BYOL is pretty much part of all discussions today with all businesses. So.
Okay, so that's getting solved. And Adesh, what about
Yeah, I think when we look at some of the tools that we have, whether it's the compilers or the libraries or some of the analyzers that we have in Intel from a high performance computing standpoint, yes, the license can be extended to the cloud as well.
So
Yeah.
basically, maybe let me come to NSCC as well on this one, because let's say you have a customer, right? GIS or someone. Sorry, I keep picking the name, but they have a certain, let's say, a license that is given to them. Say some expensive license, right? How does that work? Has it been easy to sort of take that license and run it on your premises, or it has been a very difficult task at the moment?
We have to take take it on a case-by-case basis, because there are certainly in the scientific and research area, there are a lot of different license models which are not commonly found in the commercial sector. But certainly, like things like Star CCM have a power-on-demand licenses, and where that's, if a user has that sort of license, then we will set them up with that license running on our infrastructure. So yeah, certainly some users do bring their own licenses for software, but it's difficult for us to provide nationwide licenses for expensive licenses for commercial software to all of our users, because not all, when it's only going to satisfy a small number of them. So I think it's the different research groups and things have to take the lead on procuring those licenses, and then we work with them to be able for them to use those licenses on our resources.
Yeah. Sorry, Nelson, you wanted to say something?
No, I said as an application provider, I can definitely work with you for nationwide.
Yes. So Altair are very good. Yes. So yeah, there are cases where we have national licenses, but on a sort of but there are other applications.
Yeah. No, it's understand it's there are challenges. Yes.
So I have a question, something very different, Raj. So you're seeing a lot of new verticals which are coming up. So say let's take an example of medical devices, or you take the automated driving assistance system, and then probably some traditional verticals like oil rigs, where there's a lot of data which is generated at the edge. So what kind of HPC infrastructure would you recommend these kind of newer segments which are actually coming up, whether it is on-prem, whether at the edge, cloud? So what's your
Fantastic question. So let me repeat the question for everyone. So the question is that, as we know, there is a huge demand or the IoT is happening, right? The data is being generated from various different devices in oil rigs or factories and agriculture, or forests. So what is the right type of HPC infrastructure that is required for this kind of workload? I believe that's the question.
So yeah, that's a good question. So I think there will be more and more interest in edge computing, is what we call it, right? And edge computing can come in different forms. So we have customers, as an example, that in every store they have, and they have hundreds of stores, they have 4 racks of compute. And so, obviously that requires at least a data room, and they have to worry about cooling and all those things we just talked about before. But the store itself is able to do a certain amount of analytics on its own, and be able to even change prices and things like that when they want to move a certain amount of their product. At the same time, they have it's a cloud, so they can also get information from headquarters, if you will. So that's an example of an edge computing situation, but you've got a pretty reasonable environment. On the other hand, in a car, like autonomous driving on an oil rig, these are more extreme environments, requiring density, requiring a kind of compute that can be more, resilient to that kind of environment. And so our Edgeline product is an example that we have deployed in kind of those situations where it's met. We have actually a demo where we throw that Edgeline 8000, we throw it into a pool, swimming pool, and it continues to run. And so you can take things like immersion and things like these, not to cool it, but just by accident, that can happen. And so that's a more extreme environment. So I think it goes back and forth depending upon what your edge really is.
Yeah, let me add to, let me add to this a little bit also. I don't know if you have heard about swarm learning. There is a newer concept, was published recently in Nature, and our Singapore's own Dr. Go Lim has been involved in this, and I'm going to talk a little bit about this tomorrow at 2:20. There is this newer style of learning getting developed. Just like what you say, there are lots of devices generating lots of data. It may not become useful to sort of send all the data back to some cloud and then have analysis and then send back the learning. So the idea is that you have learning itself on the cloud, on the edge. So you have all this learning, and you are able to just share the learning instead of having to share all the data. And that's sort of in a very nutshell, but you can do some Google or YouTube and learn a little bit more about the swarm learning, and I'm going to talk a little bit about it tomorrow as well. But there are newer ways of tackling this. And what will happen is that this will continue to develop. There will be, as I said, there's a new method to sort of handle this sort of stuff. There will always be this thing like you saw with NSCC that they still need to archive and store the data for long term, and then all the traditional HPC techniques come in. You know, you have your the likes of DMF, which is a tiered software to manage your data for ages that you want, and there are all of those things comes in when there is the data is big and so on, and when you require lots of computing. But there are newer ways coming in as well. You have any follow up? Yeah. Yeah.
So, what's your take on how the storage technologies are going to evolve, considering different workloads? So, traditional AI, HPC, data analytics, and storage is an important thing.
Yeah.
There's a lot of focus on compute and
Yeah. So again, for everyone, the question is that, we've been talking about compute and there's a lot of discussion about compute. Well, what about storage, right? What's happening with the storage, and is there anything new that we're doing in terms of storage?
Well, I think so you're right. So workloads do stress storage in different ways. For example, a lot of HPC workloads tend to generate a lot of data and want to write it out. Whereas a lot of AI workloads are a lot of reads and writes back and forth as you're, bringing in more data, writing out model data, bringing more data, and so forth and so on. So it's a different type of footprint. Depending upon what that workload looks like, you might want to have a specialized storage for it from that standpoint. So our luster is probably more oriented toward writing than it is necessary to reading. And it's notorious for its fast rates, but slower reads from that standpoint. PFSS is actually more of a mixed type of file system. There are other file systems out there as well that handle Weka as an example, because it's a flash-based file system, so you have that advantage of flash performance. So again, depending upon your workload and how well that does would depend a bit on your storage. And we have, a lot of folks in our organization in the field that can help guide you from that perspective.
Thanks, Bill. Anything from NSCC in terms of, do you see this kind of new storage requirements or?
For me, I found that the storage technology has been stagnant. There's not much new development. It's just about the media speed. I mean, from good old day, tape archive, spinning this. What else?
I think, sorry.
No, I was going to talk a bit from an applications perspective and a workflow perspective. Is you saw from Paul's talk that there's a lot of data sitting there, but it's important to have, if you could have the data that you're going to use in your job sort of already pre-cached in the nodes where they're going to run, and maybe a thin layer of a either in-memory or flash-based file system for fast I/O within the application, and then once the jobs are finished, getting that data away from those fast, expensive file systems into some more longer-term archival type storage. I think tools like DMF try to do that at the system level, but if you can work that into your application workflow instead, then I think there are a lot of advantages to be gained there of needing less of the very expensive storage and being able to have just a large amount of the archival storage and intelligently getting the data so it's in the right place at the right time when you need it in the fast file systems.
Thanks. I mean, I guess this also kind of comes to that same point that, we talking about the cloud versus on-prem, that when you have lots of data and the movement and that sort of issues. I don't know if anyone else in Intel has anything in this space.
Yeah, but that's a very interesting point you bring up. Your point with respect to the innovation on compute is definitely very fast, and innovation on storage does take a while to catch up. And I think it's a recognized problem, and the industry, Intel included, are looking at technologies of how we could make the data persistent and non-volatile, while to the point that you mentioned, how do you bring the data in closer to the compute resources, closer to the application, and reduce the latency, right? And there are technologies that we are working on. One good example is Optane technology, which allows you to have large caches of data on different tiered architectures closer to the compute resources. And that gives you the ability, it gets persistent, it gives you a fair amount of storage capacity, and from a cost perspective, it's definitely cheaper than having an external storage. But I think those technologies need to evolve. And I think we are probably at a nascent stage of newer technologies that we see evolving from a storage standpoint. But I think it's a very interesting point you bring up. At some point in time in the future, that you're going to see, and we believe that there's going to be this from a memory architecture to storage, there's going to be this somewhere in between kind of area where you will have persistency at high speeds and high capacity as well at a very low cost. That's from a hardware perspective. But the point that Bill mentioned with respect to file systems, that's also evolving in ensuring that the data remains coherent, data remains, whether it's structured or unstructured data, has a fast access to execution resources.
You brought up an interesting point. I mean, I remember having this discussion on persistent memory stuff that you have, and we have seen. I mean, you have seen some early adopters, especially in the case of manufacturing. Is that what you? Where do you see people are using this more? Like which segment?
From an Optane perspective, yeah, I think we have seen it in financial services, where customers have been able to move some of their existing workloads that they're running in a traditional architecture into a more cohesive architecture, where they are able to bring in fast access data in an Optane in an Optane tier, and then move some of the less access data into the traditional storage. That kind of architecture is evolving, and we've seen that in financial services, in banks. We are also seeing it in manufacturing. We as a company in some of our manufacturing fabs are using it for some of our EDA designs as well.
Okay, so we have 15 minutes. Again, any questions from the floor? No. This was sort of, again, another question that I had planned, and to just understand at least that, okay, we know there's going to be maybe hybrid environment. And in your experience, what are the key challenges, let's say, even for that 20, 30%, whatever the % people are trying to sort of maybe use public cloud, what are the challenges in using public cloud for HPC and AI?
You want me to go first? Go ahead.
Oh, you want me to go first? Okay. So I think, and certainly I've had specific customers that have experienced this, that in general, they have tended to go to the public cloud because it was a directive from either their CEO or their board of directors or whatever, without necessarily understanding what that might involve. And typically, they've had, when we talked about multi-cloud earlier, they've had the experience that they haven't been able to migrate all their data or their applications to the cloud, which means they've got the public cloud plus they've got on-premises. The public cloud has tended to be very expensive. And then at the same time, they're having to maintain their on-premises resources because they haven't been able to migrate it all. And then at the same time, the public cloud is not an open thing. So once you moved into GCP, for example, it's very difficult to move to AWS. So you have no leverage. It's not like, You know, if you're a customer today and you do a new RFP, you can open up the RFP and have a number of bidders. In this case, your infrastructure is now Amazon's infrastructure, and so if you want to move that, then it's very costly to move it from that standpoint. So you do use your leverage. So public cloud is not an open type of thing to a lot of customers. So
Great answer. Yeah. Any insight from NSCC?
Yes, so I agree with most of those statements, and there's a sort of data has its own gravity as well. So your compute tends to go to where your data is, and if your data is in the cloud, then your compute will get sucked into the cloud. But I will also, there seems, in some people's viewpoint, sort of cloud seems to be a magical thing where you just move it to cloud and it just works. Whereas you still have some of the same problems in terms of application performance and scalability and portability of your applications, and yeah, you still have the same issues. But now you're trying to maintain application portability across multiple sites, multiple infrastructures rather than just on-prem. But I think I had one other, but I forgot what it was. Yeah, the cost optimization and the lock-in I think are the two things that most stick out.
Okay, I've received a very interesting question, so let me ask some of the questions that I've received.
Yeah, one thing I will add is that there are situations where, for example, the data that you're working with, you want to share, is by itself in the cloud. So if you look at some, for example, weather data in the United States will more or less be put up in the cloud from that standpoint. So then the data is already there, and if you want to use the data, you can either use applications in the cloud for that, or you can use your own application depending on what you want to do with it. So there are some cases where it makes more sense because someone else is paying to put the data up there. You know, so if you're just a user of that data, like genome data is another example. You know, it's already up there. I could just use it, kind of thing. And so, but someone else is paying the bill, typically the government. So,
yeah. Okay, I think I have a very interesting question from the audience. So one of the question is that, would we see more a rise of containers because of this? Because now, whether it's on-prem or on cloud, you know, or people sometimes want to move things around or whatever, will we see a rise of containers instead of the physical servers for the new HPC deployments?
Well, I think it's not just public cloud versus on-prem that is driving that. I think it's a whole, even if you're solely on-prem, then containers make a whole lot of sense in a lot of cases. I think the way that people write applications now, bringing in a whole lot of dependencies on packages and bringing them together into applications means that even for traditional HPC applications, then running them in a container makes a lot of sense. But it just gives you the extra flexibility to then take that container that you are running on one site and then move it to either a different center or into a cloud to run it. It doesn't solve all of the problems.
Yeah.
There are still particularly in HPC, where we're running high-performance interconnects and things at low-level kernel pass-through and things where you're not necessarily going to get portable containers running across on your premise and the cloud.
And the cloud.
But yes, they are a really good technology, but they're not the answer. But they're a good part of the solution.
Yeah, I may just want to add on this. Whoever has asked this question, good question. Containers, yes, will grow, but the physical server in general, I mean, there is also a very a big importance of that, especially when it comes to like the compute nodes, that where you want to run the job, you want that speed, and you don't want that latency and everything that comes in with a little bit of container stuff. And just the demand is keep on growing. So it's not that we are going to see that, oh, we are selling less physical servers. I think we're going to just continue to sell more and more. There was another question which was more about the cost, but I guess you guys have covered it. So the question was more about, is the cost preventing the adoption of cloud? And I guess we have kind of answered that. And I would say that cost is a big factor. If it was too cheap and it was super easy, yes, things would have already moved to cloud. We have already seen that actually things are not very cost effective to move in the cloud. So I think that kind of answered, and Nelson and others have answered as well. There is a totally different topic, because it doesn't matter what the topic of panel, there is always a question which is a little bit different, and I welcome this anyway. So how do you see quantum computers working with supercomputers? What's especially NSCC strategy about quantum computers? So that's a question for NSCC.
Yes, so we recently signed a partnership with CQT and HPC in terms of the National Quantum Computing Hub. So we are there involved in quantum computing. We see CQT are providing the expertise, and we are there as a operational data center to try and get that out to our users. I think, yeah, quantum it's blowing up right now. It's very hot. I do see real use cases emerging where it's being used to solve real problems. Yeah. I think there's a long way to go before it becomes mainstream.
Absolutely.
But the types of problem they're trying to solve are the same sorts of problems that are complementary problems to the ones that the researchers are trying to solve on our conventional HPC systems. So it makes sense to try and co-locate them together, both in terms of having you need the right sort of people who can understand the complexities of the problem and get from the end user problem to actually something running on the quantum computer. So HPC centers are well used to taking end user problems and making them run on conventional HPC. Yeah. It's a similar problem, taking a use case and make it run on a quantum computer. So I see overlap in the types of problems that we're trying to solve. Yeah. And yes, I see, yeah, it's starting to come into maturity in terms of the actual usability. So yeah, it's certainly one to watch out for. But yeah, it's not going to be applicable for all the same problems that happen on that we're solving on traditional supercomputers, but it will. There are use cases where it's going to be a lot better. Yeah.
Anything you guys want to add on this? Let me add something on this, like on the quantum computer, and I'm going to touch a little bit on this in my talk tomorrow as well. Right now, quantum is very difficult just to even host a quantum computer, right? Trying to run at -273 degrees and absolutely no disturbance or vibration, right? Even the footsteps can't use that. So what's happening and what's going to happen, I think, is somehow people have to figure out a way to have some sort of a quantum computing in the normal environment, like a room temperature or something like that. And as crazy as it sounds, but I think there is a company in Australia I know, it's called Quantum Brilliance, I guess, and maybe, I don't know if you guys have heard about it or not. At least they try to claim that they are having like a GPU-style quantum computing sort of device that you can use that or in addition to your computing and try to solve your problems there. So I think there's a lot more to be done in there. Okay, I think we have run out of time, but there is one last question. So let me just, because we still have a bit of a time overall. Okay, what's one good thing that is good about public clouds? And what is that you would like to see that is offered by the traditional on-prem companies to improve the on-prem experience. Yes, Nelson?
The flexibility to move up and down, right?
Yeah.
In terms of capacity and capability.
Yeah, yeah. So definitely, and I don't know how many of you have heard here, but there is something called HPE GreenLake, which is kind of on-prem cloud, where we offer the same model that you can have as many nodes as you want, and if you stop using those, and it just goes down, and then your bill starts to come down. So there's something very interesting happening from HPE in that space, and that's a great point there. Any other point from what's good about public clouds that you'd like to see on-prem?
I think what I mean, kind of leveraging your statement is the fact that it is a fast way to get started. So if you need to start today, then you can go and start and get some work done from that standpoint. At the end of the day, even with our GreenLake, we have to typically deliver something.
Yeah.
So now we're shortening up as much as we can that delivery cycle. But if you just need that, suddenly you need to do some analysis and you need to get on your boss's desk tomorrow morning. You need to have an instant resource that you can get to. So that's certainly one of the advantages of it. So it's a lot about what your cloud behavior is. Is it what the one gentleman was saying is it kind of constant, in which case it makes sense to keep a lot of that constant load on prem, or is it very jagged from that standpoint, and it goes high and then you have none that goes high again? That's a better cloud, a cloud situation sort of thing.
Yeah. I also feel in that space, as you said, that it's easy to start, but I think it depends on what you really want to do as well, because I've thought about it. If someone knows that they want to run this model on 8 GPUs and they only have 2, and they know the exact spec and this is all they want, yes, they could quickly go run it on the cloud and come back. But if let's say someone says that, okay, let's do HPC, they still have to think now, okay, I want this, this, and this, and then they have to go and talk and figure out with the cloud provider, because they may not have it all available. They may want a specific CPU with a certain amount of memory per CPU, and then you still have to kind of a little bit design. So HPC is a little bit more complex, I think. But anyway, sorry, anything else you want?
So I think sort of coming on both, not just flexibility in terms of bursting and load and things, but flexibility in terms of the configuration of the software. Right down to the system level. So you come to what can be quite infuriating about supercomputing centers is that everyone you go to is different. And they're very, and as a normal user, you're very rigid in terms of what they offer you. Whereas if your supercomputing center could just sort of rapidly spin up dynamically spin up a cluster of a dozen nodes running a particular OS with a particular scheduler, and you could just go in there and partition themselves internally like that, then and offer that level of, then that would be nice. But there are reasons why that's.
Just like to add on to some of the comments from the panelists here as well. I think the good thing about the public clouds, it's a consumption-based IT. Right. You pay for what you consume, and I think if we can get that kind of model down to on-prem, that'll be fantastic. I think GreenLake is a great example of taking that consumption-based, what cloud service providers offer, down into on-prem, and then making it even better by creating a hybrid structure with multi-tenancy, where you have a single pane of glass through a management platform where, irrespective of where the workloads are hosted, whether it's on GCP or Azure or on Amazon, or on-prem as well, you have an ability to charge, from one single source. And I think GreenLake gives you that kind of flexibility. So if there's one thing that I would say what is required is that ability for customers to have a consumption-based model on-prem.
Can I?
Yes, please.
So consumption-based models are good, but part of the remit of why NSCC exists is that to give the ability for our users to run massive simulations which they can't run elsewhere within, and so it's not about providing just bang for buck consumption. It's about providing an ability for our researchers to do the types of simulations that they need to do cutting edge research, and that runs a bit counter to the sort of consumption based sort of charging. So I agree with you that it's I would there are there are pros and cons of the thing. So just as a counterpoint to that,
I'll give an example on this because I've personally talking to a customer. This was an oil and gas customer where they need to do a run. Whenever they do the run on the cloud, it costs $20,000 to do their run. Okay, so that's okay because the CIO has said that go to the cloud and that's where you do it, right? So they go to the cloud and they do the run. Now, when they had on-prem facilities, they used to constantly in between tickle something, change the config, think about a different way, and then they used to run it, and no, it doesn't run very well, so okay, fine, they go back to what they were doing. But they were constantly playing with things when things were on-prem. They were used to do that. They have stopped completely doing that because they're scared that if they try something and then it doesn't work, there's a $20,000 wasted. and CIO may not even know, but they just feel guilty that I'm going to, or somebody might going to say that what's going on here, right? So there is a lot more scrutiny when you actually go to a public cloud for a large run with HPC. You are scared as a user to make sure that your run is very good in the first instance. It's like a little bit in Singapore as well. If you don't own the car, then you're not going to try every single different thing that might be out there in the different corner in terms of a food. You're going to just go, if you're going to take a taxi, you're probably going to go where you already know it's good. You may, if you get a chance, go somewhere far, but you're not going to always try that. It's difficult, right? It's a little bit of that thing as well. But anyway, I think we are nearly in time. Actually, there is one other question I just saw, sorry. Okay. Questions again for NSCC. Everybody wants NSCC to answer these questions. So the questions are that now there are more accelerators and more choices that are coming in the market, right? There are accelerators coming from the likes of AMD, Chhabra, and so on. Would NSCC be looking into offering this kind of variety to the research community, or they'll just stick to sort of what they have?
We're always interested in the latest technology that's coming down the pipe. We talk to all of the vendors about all of their upcoming plans in terms of the new accelerators, new CPUs, new technologies that are coming. So if it fits in with our procurement pipeline, our procurement process of when we're procuring machines, then certainly we'll look at any and all available technologies that are there.
So whoever posted that question, if it was AMD or someone else, yes, they would be happy to talk to you guys, and you can come and showcase your.
But most of the time, it's still user driven.
Yes.
Yes, we cannot buy resources for just one user.
Correct.
Yeah, and then after that, most of it like used for 1 week, the guys disappear.
Yeah.
So when we put out an RFI for our next system to all of our stakeholders, then if you really want the next latest and greatest technologies, let us know.
That's definitely very correct. So whenever there is going to be a public shared resource, it's always going to be about sort of what's required from majority of this people, and not just sort of one thing. Okay. Any other last questions from anyone? Yes. Come closer. Sorry, I can't hear you. Yeah.
There are some infrastructure problems. Right?
to move around. I think we kind of covered a little bit of it, but so for everyone, the question is, there's a lot of data generated, and this makes very difficult for people to move their on-prem data into the cloud. So what are we doing to try and make it easy? I don't want to make it easy. I want to make it hard. No. No, I think anyone sort of wants to take the. I think this problem is real, right? When there is a lot of data, and that is what I guess is hindering and kind of continuing to have on-prem need, that it is hard to move the data around, right? So all the data compression technology exists, and there are companies who actually are there, specializes in data transfers with compression and all that. But regardless of all of that, I think it continues to be a problem. It's not easy to move data. And as I mentioned before, that technology limit is one thing, that you move data and then come back, that's one thing. But then there's a cost prohibicy as well, where the cloud companies makes it a little difficult for you to take the data out. And so a constant moving of data between on-prem and cloud is not a working model, at least today. The cost is prohibitive. And I think Nick mentioned this before, that if you have moved the data into the cloud, then the data has gravity. So you're going to see that, oh, maybe I have to run my compute near to where the data is. So you're going to start getting sucked into sort of trying to run things there, and that's going to happen as well. Yeah.
Yeah, I think one comment about this is, as I talked about federated clouds from that standpoint. So then you have to worry about where your data is and those sorts of things.
Yeah.
But there are solutions that most of us are probably using today for this. And if you go into Netflix or any movie, right, what happens is that I live in Houston, Texas. So what will happen is that Paramount Plus, for example, will prefetch things that they think I will want to look at, and that will be stored more locally to me than maybe back in Hollywood or wherever it is, right? And so there are solutions for those sorts of things. No promises at all, nothing on the roadmap, but these are things that we're looking at. Again, I will talk a little bit about it in my keynote tomorrow, but yeah, so that's something.
So in order for that caching to make sense, then what would possibly work would be, so we've got the DMF set up in NSCC, where our DMF was extended into the public cloud infrastructure and sitting inside their public cloud infrastructure. So there's no, but it's we have our network connection there, and it's sitting inside there. So we can get all the data
automatically there
into the cloud, and then if it's inside the public cloud infrastructure, then there's no, then it's readily accessible within that availability zone or whatever within the public cloud, and then that
becomes easier.
That becomes easier, but it requires the public cloud provider to let us.
Yeah, and I guess this is where you are, in a way, a cloud for the universities and stuff, and you definitely probably already thinking about that. Hey, you want to have your users, a node where they have sort of like a DMF infrastructure, and whatever they're putting in, the long term automatically coming into to you guys and so on. Okay, I think we are at time. So thank you so much for your participation, and thanks for coming in, and thanks for great questions.
Thank you.
Big round of applause for our panelists, please. Okay, there is a closing remarks by Bill. Obviously, we could use your mic. I think it doesn't matter.
So certainly this concludes our forecast for today. For those who have joined us in person, we thank you. Hopefully this is the start of a different way of doing business that was like things were a few years ago, and certainly appreciate all those who dialed in remotely as well. I understand there was a large contingent that did that. We continue to advance our portfolio around high performance computing. I think we had some good presentations around that. Again, we have a high end, we have a mid range. and also a lower end compute capability, whether they're standard formats or more unique formats. We are looking to the future in terms of how processors and accelerators are going to change and get more powerful and need to be cooled as we go forward. So we have some follow there as well. We are now in our third year of the Cray integration from that standpoint. So now we're seeing some of the technology that we've are going to be bringing out and making more broadly across our product line. So things like Slingshot, the interconnect optimized for HPC, the Cray programming environment, and some of the other Cray software assets that we'll see, Cluster Store and PFSS, our spectrum scale product. These are all going to be available much more broadly across the product line, so you don't really have to make choices. And at the end of the day, we're going to be the open provider with a lot of choices in terms of processors, accelerators, software, and these sorts of things as we go forward. So again, thank you for your attention today, and have a good rest of your show. And I have a keynote at another plenary tomorrow, and as does Raj as well. So please join us there tomorrow as well, and have a great evening. Thank you.